Hey guys, let's see. Today we're doing trees, and I'm actually streaming to the right place this time, which is epic. Let's see. Let's do some basic setup. How are y'all doing? Whoever is here right now. Wait. This is showing up, right? Let me just see. Yeah, okay. It says it's running. It says everything's good, I hope. Alright, so, do a quick thing here. As usual, notify the Discord. Okay. That should work, right? Yeah. So, say your name, please. All right, Crystal Violet again. How are you? How are you doing? Okay, so basically the plan is we're doing tree topics today, and currently there's a round going on, which is kind of an issue, but whatever. This will still be available as a VOD, even if people miss some of this, so it's probably fine. Can't exactly reschedule. It's not perfect to do so I'll leave it as is. So yeah, first I'll go over a basic introduction to like what a tree is, kind of how it works, how to operate with it, and then we'll just get into problems. This mashup right now is available in the description, and yeah. So that'll work. Yeah, okay. So the reason it shows this green thing right now is because I've kind of like, okay, these problems I've kind of set up this mashup differently. I've sort of handpicked these ones to make it kind of more interesting. But at the same time, like I don't perfectly remember all of them, so there's still enough like live solving to be done. But yeah, this one, it shows I've solved it because I have solved it before in some like old contest or something. But I mean, it's still fine. Like there's still a lot of things that can be gone over, like the sort of techniques and stuff that we use for them. Okay, so first of all, let's do an intro to trees. Basically, so what is a tree? Draw a little underline. So a tree is, first of all, a special form of graph. And okay, so a graph is basically, it's defined as this sort of like visually represented thing of a set of vertices and connections. So a connection runs between two vertices, it's called an edge, and basically a lot of things are defined based on these connections. This is any arbitrary graph. So that's it. These are vertices, these are edges. That's all a graph is. The way we use graphs is like asking certain things about it. For example, these graphs, they can form connected components. That is like it's subsets of vertices where in the subset there's a path from every vertex to every other vertex in the subset. That is called a component. And a path is essentially a sequence of vertices such that between every adjacent pair of vertices there's an edge between them. So like basically you can just, if there's a path from this node to this node, you can go through a bunch of edges until you get to this one. And then a connected component is a subset of vertices where all vertices have a path between each other. And then, for example, that's one thing you can ask about graphs. But all the graph is just a bunch of vertices and edges. How long will it be? I don't know, probably a few hours. I'll try to get through the whole mashup. I'm not sure that's going to be possible, but I'll do what I can. Alright, so a tree is a special form of graph. let's say it has n vertices. And by the way, I may use vertices and nodes interchangeably. They're the same thing, basically. So if it has n vertices, then it has n minus 1 edges. So these are not trees, these are general graphs. I'll draw a tree right now. And it's kind of like, could be thought of like this. A good way to think about it is in like the top-down manner, where you have some vertex at the top that sort of dictates everything else. And then, so you have n minus 1 edges. As you can see here, it holds for this tree. We have 7 vertices and we have 6 edges. And so it's kind of like universally true. So we have n minus 1 edges. There are no cycles. And what that means is a cycle is a path that starts at one node and goes through a bunch of edges to eventually get back to that node. But trees don't have cycles, which means what this means is that for every node, there's exactly one way to get to every other node. For example, like here, there's only one way to get from the first node to the second node. You can't go through any other set of edges and do some magic to get there in a different way. So that's another property, that every 2 nodes, like, it's basically unique paths. There's a unique path from every vertex to every other vertex. Let's see. A tree is also connected. In fact, I'm going to move this down, and a tree is also connected because, like, that's just how we define it. And connected means that the whole tree is in a single connected component, which is kind of implied from unique path. The fact that there's a unique path from every vertex to every other vertex means that there's a path from every vertex to every other vertex, and therefore the whole thing is a connected component. And there's one more property, that if we represent a tree like this, basically, like, if we consider the levels of the tree, like this is level 1, this is level 2, this, I kind of drew this badly, this is level 3, and this is level 4, then every vertex, except for the one at the top, will have exactly one parent. That is, some vertex that's above it and has an edge, like, to it. Which is kind of a cool property because it lets us do like certain things with the representation. So basically every node except the top, which is called the root node, has exactly one parent. Okay, so the first thing we can talk about in this stream is how do you, I'll solve problems. The first thing we should talk about in this stream is how do you identify a tree when you're reading a problem? Like some of these problems, I'm sure they don't exactly say you have a tree. For example, in this problem, there are n cities and m minus 1 roads. So you have this condition, check, and this condition. And then each road connects 2 cities, and we can reach any city from any other by the roads, which means we're connected. So, like, the question is, does this imply a tree? And, well, it just does. So the cool thing about the trees is that, like, these 3 conditions are kind of related to each other. If you have any 2 of these conditions satisfied, then you have a tree. And that means the 3rd condition is implied. So for example, in this problem, we have m minus 1 edges, and we have a connected graph, and that's enough to claim it's a tree. I'm not going to prove that on stream because it's kind of annoying, but basically, like, that's how you do the representation. Also, making a claim like this, either of these being satisfied is enough to also have a tree. If you have a parent representation of a tree, where every node except Actually, no, that's not true. Never mind. Maybe not this one, actually. But having a unique path from every node to every other node is enough to imply a tree. So either greater than or equal to 2 of these, and like maybe this one too. That's also a possibility. And I think having let's see, it's like having this one almost implies a tree, but like there's sort of messiness because you can do something like this and kind of have a cycle going on. So if you also claim that it's acyclic, then it'll be a tree, I guess. Acyclic or connected will make it a tree. Actually, no. That also requires n minus 1. Okay, ignore never mind. I can't explain this. Ignore this part. Basically, just like if it says it's a tree, then they'll have each node will have exactly one parent. Okay, I'm gonna answer chat now because that's sort of the end of the section. 5K sub special. Maybe this Friday. I'm gonna try and sync it for the weekend so it can get views as always. How to take input as tree? Well, that's basically you would store a tree as like any normal graph, where for each node, basically you would so say these are, I'm gonna label these nodes 1, 2, 3, 4, 5, 6, 7. Basically, for each node, what you'll do is you'll store the nodes that are adjacent to it. That is, the nodes that it has an edge to. So for example, 1 would be adjacent to 2 and 3. And this would be a list. This would be a vector or whatever you want. 2 would be adjacent to 1 and 4. 3 would be adjacent to 1 and 5. 4 would be adjacent to 2, 6, and 7. 5 would be adjacent to 3, etc. It goes on. How long is this session going to be? I'm not sure. Yeah, probably until the end of the mashup, something like that. How many did I do daily? Not many, actually. It was sort of like spending a long time on use code training, which is one way to do things. Number of nodes is non-decreasing order going down. Yes, actually. No, wait. I mean, not necessarily. You could have something like this, and then like this, and then just have the tree stop short. So like this would have one layer, this layer would have 1, this would have 2, this would have 1. It depends on the leaves. Does every edge over n-1 edges add 1 cycle? Not exactly 1 cycle, because I could do something like this, and then like this, and then that would add, this edge we have here would add 2 cycles. It would be like this one, that triangle, and this big diamond thing. So the first edge will add exactly 1 cycle. Others may add more than 1. It sort of depends. Let's see. Why is it important to study trees separately? Well, trees are they are a special case of graph, but there's so much more you can do with them than graphs. Like, for example, you're going to see in this contest, there's a lot of cool things. Yeah, adjacency list. There's a lot of chat. What sites do I follow to learn algorithms? Usually stuff like use code training and code forces. There are a lot of useful blogs and things. Yeah, this is the intro right now. Okay, so that's basically it. I'm going to leave this open just because why not? I'll get rid of these notes though. I'm going to leave this open so we can refer back to it and sort of reference it. If you want to take a screenshot or just save this point in the video, you can if you want. Okay. So, let's see. Is Codeforce alive? Alive enough to load the problems? Okay, cool. Alright, let me open a new paint. And we shall get started. This one is a 1400 right now. I kind of made this mashup harder. Like, it's a bit. It doesn't have the easier problems that the DP mashup had, so it's kind of a bit harder. But it's whoa. Someone solved this. Nice. It's kind of a bit harder, so yeah, we'll see. Okay, I'm gonna do the thing. What the hell? What is this? Why do I don't see this on mobile. Did it get removed or something? I guess it did. Let me see. Copy the mashup link. Aaron, that link probably won't work because you have to be invited first. So let's see. I'll do this and then pin that because I have this newfangled ability to pin messages. How cool is that? Alright. Am I covering all concepts? Heavy light decomposition? No. Well, I already have a video on that, so that's kind of like pointless to do here. Binary lifting, I will. Yes, that's this problem. Okay, first we have this problem called queen. You're given a rooted tree, which means we don't even have to check these things. They just straight up say we have a tree. With vertices numbered from 1 to n, a tree is a connected graph without cycles, and a rooted tree has a special vertex called the root. Yes. And ancestors, the vertex I, are vertices on the path from the root to the vertex I, except the vertex I itself. So basically an ancestor is, for a given vertex, it's any other vertex that's like above it. So for example, this one and this one would be ancestors. But like another way to think about it is if you consider this vertex and then you consider its path up to the root, which we already know is unique, then essentially an ancestor is going to be all of the vertices on that path to the root. Basically just everything that's directly above this. If you think about the tree in the top-down way. And the top-down way meaning that you like fix the root and then put everything adjacent to the root at level 1 and then everything adjacent to those at level 2 and so on. So like this. Let's see. So you're given a tree. You notice that some vertices do not respect others. If Ci equals 1, then the vertex I does not respect any of its ancestors, and if Ci equals 0, it respects all of them. He decided to delete vertices from the tree one by one. On each step, you select such a non-root vertex that does not respect its parent and none of its children respects it. If there are several such vertices, you select the one with the smallest number. When you delete this vertex V, all children of V become connected with the parent of V, and they have this nice diagram that displays what happens. Once there are no vertices matching the criteria for deletion, you stop the process. Print the order in which you will delete the vertices. Okay, so first of all, doing this naively isn't going to work. And the reason is, even if you had some efficient way to find out which node you would remove, take a tree like this, like a really long vertical path, and then at the bottom of this, you have like a ton of vertices. And then say the numbers are so that you'll delete this one first. So then you'll have to attach all of these vertices to the higher node. And then say you delete this one next. Then you have to delete all of these vertices, and then so on, and then so on. So every time you're going to like reattach these vertices to the higher up node. Which means if this is like 10 to the 5th or something, and this is like 10 to the 5th, then it's definitely going to TLE. So naively simulating the process isn't going to work, which is why we have to be more efficient about it. So the idea is, first of all, the first condition says that it does not respect its parent. And the only way that's possible is if its value is 1. So say it has some parent. The only way this is possible is if its value is 1. Because otherwise, like, it's just not going to work. Because if its value is 0, then it by default does respect its parent. So we're only interested in vertices that have values 1. And then the next part is, yeah, I picked this problem because it has sort of observations. And the next part is this. So for a vertex to be removed, all of its children have to also not respect it, which means all of its children must also have value 1. And then when you remove this vertex, all of its children are then going to be children of the higher vertex. Which means, like, if this one is also sort of 1, then, like, it doesn't exactly matter what happens. It doesn't matter if we remove this one or we remove this one first. Because either way, if we remove this one, that implies that this one is 1. And it also implies that all of its children are 1. Which means that when we remove this, for this vertex, if it was already removable, then it will stay removable because the children of the vertex that are under it are still going to be 1. And that means that removals don't actually change anything. That's the observation. And the reason this observation is so nice is because that means that we don't have to modify the tree at all. If a node is initially removable in the first form of the tree, then it will stay removable. So we only need to check for each vertex if it's initially removable. And doing that is simply asking if its value is 1, and if so, are all of its children 1 as well. And if it has a single 0 child, then it has something that respects it, and therefore, like, you can't remove it. Like, you couldn't remove it anyway. So yeah, that's basically the idea. So you essentially, the strat is just to check each vertex if it's removable, and then like print them in sorted order or something. So first of all, I'm going to do the fancy thing where you update the subscriber count always, because that's just how it works. It's a long-standing tradition. Before we write any code. Okay. Now, this is going to be, by the way, I opened this because Codeforces was being down, but I'm going to use the normal problem set thing. So how do you like implement a tree in code? This is the first question. Well, basically, what we need to do is, first, we need to get the vertex, and second, we need to get all of the children of a vertex. Like, somehow we have to know what these nodes are. So the idea is like we're very close to already being able to do this. Say we have the adjacency list representation, where essentially, for every node, we store the other nodes that are adjacent to it. That is, the nodes that have an edge to it, kind of. And like, look at this. Almost all of these nodes are children. The only issue is that the parent is also part of the adjacency list. But the cool thing is that we have exactly one parent no matter what. So all we need to do to find out the children is figure out which one is the parent and sort of ignore that one. So there are a million ways you can do this. First of all, you can start at the root. You can explicitly compute these depths, and then to ignore the parent, you just ignore the one that has a higher depth. But like, don't do that. That's sort of annoying. There's a much better way to do that. What you can do is start at the root. Let me draw a better tree, because this one's kind of bad. Start at the root. Binary tree, that looks fine. Start at the root, for example, here, the top vertex, and you're given that the root is 1 in this case, I think. Wait, is it? No, you're not given that the root is 1, but you know what the root is. So start at the root. And then a root doesn't have any parent, so you can sort of like just, all of the nodes in the root's adjacency list are going to be its children. So say you visit one child. Okay, so first you're here, and then now we're here. Okay, so we need to find out the parent of this vertex efficiently. But like, we know that we just came from a node that's higher than it, which means that we just came from the parent. So our current path is like this. And if we store the fact that we just came from the root, then we know that we want to exclude the root from the list of the children. So like that's the basic idea. So now we visit this vertex, and every vertex that isn't the root in the adjacency list is going to be a child. Then we look at this vertex as children. So we go here, and we notice that we just came from this one, which means that it's going to be a parent. So in this case, it has no children because the only thing adjacent to it is its parent. And then we look at here in the same way, and then we sort of like backtrack up the tree and then start looking at the root's other children. So we look here, we exclude the root because we just came from it, and then we find the children, and then say we go down here, we exclude the vertex we just came from, and then everything in here is a child. This is how you would represent like a tree. And notice that excluding, and then you sort of like recursively go into each of these. This is like the basic definition of depth first search, sort of. You can also do it other ways, but this is the easiest way to do it. So I'll explain how to like recursively do the things in code. It turns out to be quite simple. But let's see, I believe that's enough. Definitely for this problem, that's enough. So the idea is as follows. First of all, let's read an n, obviously. Then essentially we're going to store the parents. Okay. Actually, this would be how you handle a normal tree, but this sort of has weird input. And this, I'll explain in the context of, this is more of a general way to handle trees, but in the context of this problem, it's going to be different, I think. Something like this. So basically this problem tells you, like for example, this vertex has this node as its parent. And then this vertex has this node as its parent. And so it sort of like tells you all of this. So the way we can sort of take advantage of this is we can say, if a vertex has this as its parent, if this is the parent of this vertex, then if we reverse it, we say this is the child of this vertex. So that literally just tells us what the children are. Like for every vertex that has this as a parent, we just put that vertex in this child's in this vertex's like list of children. So that sort of just works. Like so we can store a vector for each node of children. And then basically we say oh, these are 0 indexed? Are they? No, they're not. Okay. So if x is not equal to -1, then we decrement it to 0 index. And we say that yeah, so basically tells us for each vertex what its parent is, which means that we have a relation that like vertex x is parent of I, which says that basically I is a child of its parent. So it's children x dot push back I. That's how the relation will work. And then what we do from there is we say we're just gonna like put in a vector all the nodes that are possible answers. And to do that, we check if, actually wait, it's essentially checking that. So if AI is equal to, actually I'll use C to be more consistent. If Ci is equal to 1, then we check for its possibility. for each child of I, if Cx is equal to 0, then it's not possible. Otherwise, it means either it has no children or all of the children are 1, and therefore it's possible to remove this. And then, if possible, we just like stick it in the answer. And then, okay, supposedly this will work. Unless I've managed to misread the problem somehow, which is of course a possibility. Oh wait. Okay, this should be a vector of size of the maximum number of nodes. So for example, 1e5. Actually, we can stick this in here too, and then this would be just n. Either way really works. That's not what I meant to run. It's an old program. Yeah. Get rid of this, kind of annoying. So we get 1, 2, 4. Here I think we get nothing, so we should print -1. Yeah. And then here we have 5. If ants.size is greater than 0. Else. Yeah. Make sure. Alright. Looks like it works. What do you mean nice? It's the first problem. What are you talking about? I don't have to sort because I'm going through the vertices in order. But otherwise you would have to sort. Okay. So yeah, that's the first problem. Basically, put all the children in a vector. Like, look at all the children. See if it's see if any of them are 0. If so, it doesn't work. And simultaneously, you can do all of this while processing the input. Like, you can just like check for each child if it's a 0 while in this sort of thing, but you don't like. There's no reason to do that. You can just sort of like represent it explicitly. It's sort of the way you prefer to do it, I suppose. But like, there's no reason to try and like do some messy stuff like while processing the input and things. Seg trees, probably not. I think that's sort of beyond the scope of this. Okay. When do you use struct for trees? It's sort of not necessary, I would say. Okay, I'm going to do the same thing, but sort of like, wait, what? Come on, cancel. I should have someone else do this, but I'm like, whatever. Replace pin message. Okay. So for some reason it like doesn't show the pin on mobile or something. I don't really know how that works, but I guess screw mobile. YouTube hates it anyway. Why not? So I'm kidding, but I don't know. YouTube's just weird. All right. There are n cities and n-1 roads. So again, yeah, we're like looking at this problem. There are n-1 edges. We have that confirmed, and we can reach any city from any other by the roads. That means it's connected. So we have 2 of these conditions, so it means we have a tree. And generally, you want to be able to recognize trees in problems, because a tree problem, like a problem on a tree, is almost universally always easier than solving the problem on a graph. So we want to check that. Like, obviously, we want at least one of these for it to be satisfied. So we have n-1 edges and it's connected. That means we have a tree. Even though it doesn't explicitly say it, Well, first of all, it's on a tree mashup, so like, yeah, but at the same time, like, it's a tree. So, two people are on a horse in the first city. They're starting to travel through the roads, but the weather is foggy, so they can't see where the horse brings them. When the horse reaches a city, it goes to one of the cities connected to the current city. But it's a strange horse that only goes to cities in which they weren't before. In each such city, the horse goes with equal probabilities, and it stops when there are no such cities. What the hell? Let the length of each road be 1. The journey starts in the city 1. What is the expected length of their journey? So you asked for probabilities. That's what we got here. Right. So, let's see. You have a tree here. And yeah, I do right with my mouse. You have a tree here. There's some stuff here, I believe. Let's see. I'm going to intentionally make these subtrees different. So this one will be empty, for example. Actually, I'll put this here to stagger it a bit. Alright, and then you have these edges down here. So basically you have some horse or something. It's going to start in this first node. And then from here, you're going to uniformly at random pick one of these 3 vertices and then go to that one. So for example, say I pick this one. And then from here, you're going to do the same thing. You're going to pick at random one of the vertices that are adjacent to this one, except you won't visit the one that you just... Except you won't visit anything you've already visited before. So it means it's always going to go down the tree. In this sort of representation where we have a root and then we have parents, it's always going to go down the tree because this is the exact same thing we're doing in this sort of DFS. We don't go to parents because we just came from them. So in the same sense, we won't go to parents in this tree because we just came from them and we can't do that because the problem says we can't. So we're only going to children, which basically means like here from this one, we'll go only into one of these. Okay. And basically we're interested in the expected length of the journey. So this is like whack. Alright, so the idea is basically as follows. We want to find the expected length of the journey starting at 1. So, like, we're going to go into one of the children. And then, from each of these children, now we're sort of solving an independent problem. Because we can't ever go back up, now we're only solving the problem for what's the expected length of this subtree? What's the expected length of this subtree? And what's the expected length of this subtree? And how do we solve each of these? Well, this is the same problem. So now we're sort of like, imagine I just like cropped this tree out and sort of moved it over here. So now, and then I just sort of like ignore all of this. Now we're solving the same problem, but on this tree. So we're here. How long does it take to go down? Well, we can go like at random to one of the children. And both of these moves are going to take 1 move. And then from here, now we're solving the problem for each of these subtrees. And it sort of just goes down and sort of like, yeah, it goes down sort of recursively. So the reason this is cool is because, well, like, so what that means is if we know the answer for these subtrees, and we know the expected journey, given that we start at this node and we're only going down, then we can easily find the answer for this one. Specifically, the answer is 1 plus 1 because we have to take like 1 move to go down. And then it's 1 plus the average of children. The reason this is so is because of how expected value works. Basically, the expected value is like the sum. The expected value is the sum of the probability of I times the value itself. So basically, for each event, it's the probability of something occurring. So for example, the probability of going into this subtree would be this expression. And then the value I itself is, actually let's call it like AI or something. So it's the probability of this happening times the value we actually get from it happening. Which is to say, an AI in this case would be the time for the expected length of the journey for that specific subtree. So how do we break this down? This is something we can solve in the subtree. But first, it means like we have to solve this before we solve this one. So we sort of go down recursively and we solve until we get to a point where there are no children. Then the expected length is 0. Then we go up and then we sort of use that to compute the parents that we've already done, provided that we have all the children already, and so on. So AI we can find out, because again, the answer for a leaf is just 0. And then the probability of I occurring is, well, in this case we have 3 children, and each of the children have equal probability of happening, which means that it's really the sum of 1 over, like, the number of children that I has, times, actually, I'm going to call it V. The number of children that this vertex V has, times AI, where I is the child. Which is to say, it's the average. Okay, now that's how this is the sort of formula. But now we have to like figure out how to do this recursively. And like, okay, I'm gonna stop sidestepping now. This is just tree DP. Basically, the way this works is, if you haven't seen DP before, I have a stream on it. It's kind of cool. You should probably see it. So you let DPI. You let DPI represent the the expected value of length in the subtree of I. And then basically the way you compute it is using this formula. So that's sort of like, maybe it does overkill the problem. People are saying that it's also averaging the sum of all paths. I suppose that's true because, will that be true? Wait, I'm not actually, wait, why would that be true? Like, say you have something like, say you have a tree like this. Then going from here, you have a 0.5 chance of ending here, and then a 0.5 chance of ending here. And then each of these, you have a half chance of going there. So here you have a 0.25 chance of ending here and a 0.25 chance of ending here. So it's not exactly uniform. Like, it's uniform across the, it's uniform inside the subtree, but or inside the children itself, but it's not uniform in the place that you end. So either you can compute out these probabilities and sort of do it that way. Like, you can sum up these probabilities times the length of a path. That would be another way to do the expected value. Or you can do tree DP. Either way, it shouldn't be a problem, I don't think. Actually, it might with precision, but I don't know. But anyway, this feels natural to me. And then again, so it's equal to 1 plus the average of the DP values of the children of I. So, also for completeness, I'll add a 1 here. Yeah, and the way to compute average is simply the sum of the values over the children divided by the number of children. So that works. In any case, let's do this. So here we're given the standard representation of a tree, which means that essentially we can do this DFS normally where we start at 1, we go down to each of the children, and then we don't revisit the parent. And therefore the only vertices we look at are children. So let's see. So read into n, and then we'll say that we have a vector of edges for each node. Then we have exactly n-1 edges. That's given. We have a tree. So decrement them for 0 indexing. Then we just basically add the bidirectional edge to both of them. We can't we can't only add one of the edges because from this input alone we don't know which one is the parent, which means we have to make the full tree and then sort of figure it out later which one is the parent of which. And then from here, okay. Now I have problems with using doubles. I will admit. Okay, here we did this, so it's fine. Set precision and fixed. Then we're going to say that when we do this sort of DFS, I know how this function is going to go because we actually don't need the DP value, sort of. We can just sort of say current parent. We don't need the DP values exactly. All we really need to do is we say value equals 0. Then this should be double. For allow next edges cur. If it's not equal to the parent, then it's a child. So plus and child, and val plus equals DFS next, and now current is the parent of that vertex, so we sort of do it like that. If n child is equal to 0, then we have a leaf, so return 0. Otherwise, return 1 plus value over n child. So it's sort of like doing DP, but without the array, because there are no overlapping subproblems in this. We solve for each subtree exactly once, because each vertex will come from exactly one parent. So therefore, we don't have to actually store anything when we do tree DP. We can sort of just return it. And that's actually it. Okay, I will read chat while running this. Nope. So looks like it does not work. Why not? Maybe I do have an infinite loop. This is what I get for being cocky. What's happening? Am I like... Oh. What? What happened? Okay. Looks like it works. Even though I didn't think it would work because it... Okay, sure. Alright, while this runs, I'll answer questions again. Do I use a mouse to draw or drawing pad? I do use a mouse for fun. Then how... adjacency list using vector is definitely faster than using map because it's just kind of like It's like it's O of n or O of n plus m, O of v plus e to do everything kind of. Zero-based indexing just because I prefer it. Like, there's no real reason to use zero versus one-based indexing. It's just kind of like, I mean, vectors sort of force you to do that anyway. So, like, everything is zero-based indexing except for problem statements. So it's just sort of preference, really. But I just prefer zero because that's the way I learn things. Did I do discrete math? I did not. In fact, I'm taking that next semester in school, which should be interesting. How to output trailing zero? You do this thing called set precision, and then basically what that means is, like, if I look at these tests, it's going to make it so it prints like a certain number of digits after the decimal places, like the decimal places, and then to make it to, you would like say it's fixed because that's like the form of the number you want. You don't want it to be scientific notation, so you set it specifically to be a fixed like format, and then it sort of just lets you do everything. Why are these answers so weird? They're like non. Is it always an integer? No, it's not. Okay, okay. I was confused. So that's the second problem. I'm used to using long double. Or yeah. Okay, I don't know why I called it LLD. Like, it would make some more sense to call it LD, but I'm just kind of like used to that. So that would be how that works. I'm used to using long double over double just because because I just prefer to not have I'm used to using long and high values with more bits because I prefer to just not even try to think about overflow. And so I just always use the thing that probably won't overflow. And the same goes here. I don't want to think about precision issues that you'll have with not having enough representation of the numbers. So I just like make it as big as possible. That's basically my habit. Use VS Code? No, the whole point is that we don't have syntax highlighting. I'm trying to make a point with this sort of like thing that it doesn't matter what your IDE is. Maybe it does help to maybe it does help to have the what is it? Like they auto compile it for you sort of and label things, but it's not necessary, I would say. Explain at the end of the stream, how do you keep records of the tree using vectors? Sure. I mean, it's sort of like the same thing. Alright, what's happening? Not much? Okay. You have a bunch of vertices in the tree. By the way, this stream is still going, right? I want to just check code first and make sure. Yeah, it's perfect. Okay. Wait, what's the difference between VS Code and this? Like, I can make this a different color if it's sort of hard to see. The thing is, Notepad++ will let me, it will let me do the syntax highlighting I want. I just don't know what there is to highlight. Because sort of like, I don't have a problem with this, so it's fine. But if there's more you want me to do, just tell me, I guess. Okay, so you have a rooted tree. That's easy. Don't have to figure out that it's a tree. We just have a tree with n vertices labeled from 1 to n, where the root has index 1. Nice. So again, in each of these problems, we're looking for keywords that tell us that we have a tree, where the root has index 1. Each vertex v initially had an integer number, a positive number AV, or a non-negative number written on it. For every vertex v, media is computed SV, the sum of all values written on the vertices of the path from vertex v to the root. That means if we have this sort of thing, Yeah, there's this whole discussion about IDEs that we can sort of get into, but I don't think it's necessary here. If we have this sort of thing, then essentially, for this vertex, for example, we have the sum of all of these values, and then for this vertex, we have the sum of these, and so on. It's the sum of the like the values from each vertex to the root. But the problem is, oh, and also the depth of the vertex, which is just like the distance from the root. But then he erased all the array values, which is fine, but he also accidentally erased the sums. But only for the vertices with even depth. And what this means is that, so for example, we could have something like this, where we have 1, and then we have, like, for example, the reds are the sums. We could have 2, 5, 3, and 3. But then these values are gone. We don't know what they are, and that's really sad, because we want to know what they are. So what you want to do is, you want to figure out what these possible array values could be. And in doing so, you want to make it so that it minimizes the total sum of the array values for some reason. Because they don't want to check constructively, which is kind of annoying, but like whatever. So you want to restore the initial values. Okay, first thing to note, the root's value is obviously like its value of the sum. Because there's no other value from it to the root. But now, like, consider this vertex. What can this be? Well, it sort of directly depends on... It sort of directly depends on what's going on with the children. And, well, okay. So we have that this child requires the sum of these 3 vertices to be 3. This child requires the sum of these 3 vertices to be 3. And, like... So, like, basically, these things sort of have to be, I mean, this path plus whatever these vertices are has to be 3. So, like, in this case, these two have to be equal. But what can we really do for this path? We can make it anything that's less than or equal to 3, and then we can make whatever these two vertices are sort of fill in the gap. So, like, 3 minus... Let's say this is a number x, then this is the value 3 minus x, so that the sum of these two paths are 3. Which is fine. But, like, at the same time, we want to minimize the total sum. So, like, this is one vertex. Like, here's the basic idea. This is one vertex. This is multiple. So, if these are equal, we want to make this one as small as possible, because if we make... Because this is going to reduce multiple vertices, but making this small is only going to reduce one vertex. Which means essentially the idea is that there's an optimal answer where we make this one as large as possible while still making it possible. So for example, if this value is 1, then this one would have to be 2. Because then the sum of these are 3. And so the condition is satisfied. And then we make this 0. Because that's possible. But like if we didn't, if we, for example, made this 1, then this would add 2 to the answer, and if we reduce this by 1 to compensate, we would only subtract 1 from the answer. So basically the idea is we have more vertices in this group, so we want to make this group as small as possible, and that entails making this as large as possible to minimize the sum. The way to sort of succinctly represent this is, well, here we want to make this as large as possible. But like we have this sum already at 1, and we know that this vertex requires it to be 2, which means that like 1 plus this value x must be less than or equal to 2, because if it's greater than 2, this value must be greater than or equal to 0, so it's not actually possible to make this tree if this value is greater than 2. Which would suck if that's true, because that means we don't have an answer. But luckily we do. we can make this 2. So, or we can make x 1. So basically the idea is you want this sum to be equal to the minimum of the subtree of like the children's values. Which means you want 1 plus x equal to the minimum of s children. Because it can't be greater than the minimum, because then one of the children would have to be negative, and that's not possible. And you don't want it to be less because you can make it bigger. And we've shown that the optimal answer has this value be as big as possible. So the exact value you want would be the minimum over the children. Yeah, it can't be greater, it can't be less. So therefore it has to be equal. And if this value above is greater than the minimum already, then this value would have to be negative to make it work, which is impossible. So in that case, it's impossible. But the value you want to set it to is equal to, basically solving for x, it's the minimum over the sums of the children minus the sum of the parent. And then if it turns out that any of these values have to be negative, then we have no answer. So that's kind of it. We just go over the even vertices, compute this thing, and just be done. Yeah, okay. So let's see. Let's just like do that. So again, here we're given the parent representation. That means for each vertex, except for the root, which is 1, we're given what its parent is. And therefore we can sort of represent it like this. We reverse all the edges so that we store for each vertex what its children are. And this would be 10 to the 5th. So read into n. For I equals 0, I is less than n, I plus plus. Actually, m minus 1. Then this means, so we have p is parent of I plus 1. This being 0 indexed. Then children p dot push back I plus 1. And we also create a S array for clarity. So now what we're doing basically is first we have to compute the array values themselves. So we just use this formula basically. So we define this function DFS, where we basically say let's see. So the current vertex, the parent vertex again, and we DFS from the root node, and it has no parent. So LL as parent equals just the S of the parent. That's what this is. Then if SI is equal to -1, then we say that min value equals, it's at most 10 to the 9th, so we can make it like 2 times 10 to the 9th. Then for each child, cur. I usually just use v and p here, which means it's kind of like weird for me to code like this, but it's fine. Min v equals min v s child. And we know this value is not -1 because it only happens at even things. And this is -1, so every child must not have -1, like necessarily. So then Si is equal to parent minus min b. No, it should be the other way around, min b minus parent. And therefore, AI is equal to, now what do we do for AI? Here's essentially how this works. How many times have I said that for this problem alone? Say we have say the S values are, for example, 1, 5, and 7. Then we know that the sum of these two vertices is 5. And we also know that the sum of these three vertices is 7. So the value of this vertex alone is the total sum minus the sum of everything else, which is essentially Si minus S of the parent. So AI is equal to Si minus S parent. And that works because it's sort of just it's everything. We have this path up to the root, and the parent has everything on this path except for this vertex itself. So we subtract out the parent, we get exactly what we want. So AI is equal to Si minus S parent, and then ants plus equals AI. So first we check if it's possible. That is it, right? We want it to be -1. Yeah. That should do it. Si. Should be current, I suppose. Yeah. Oops. -1. Nice. Okay, so what's happening there? Have I screwed something up? 0, 1, fine. 1, -1. How? Oh, whoops. Because then I have to actually go into the children. Otherwise, it doesn't make sense. Because yeah, this is what I was doing. I was basically I had this whole tree. I'm gonna draw another tree, very hastily, and then I was here, and then I looked at this, and then that was it. I just didn't look at anything else. So of course the values would be -1. I didn't even touch them. So that's why you have to do the DFS for all of them. Still -1. How so? For each child. Oh wait. Okay, I want to do this outside. Yeah, otherwise, because that would still do the same thing, because the root doesn't have a value of -1. So it doesn't make sense to do it there. What? Okay, that's not right either. That is not right at all. Haha, what the hell is that? If children, I guess if we have no children, then min value equals would it be S parent? Wait, this doesn't even make sense. I'm subtracting the parent itself, its index. What am I doing? This makes no sense. Min S child minus S parent. Does this actually make sense? I guess it would. And so we can set this here because if we have no children, then this can be 0 because it can be whatever we want, sort of. how many mistakes am I gonna make in this one problem? If children.size is equal to 0, oh, children cur. And so we get a different wrong answer. Damn. We're minimizing the sum of AI, right? Yeah. Wait, how is SI? Oh, this would have to be the minimum value itself. Whoops. Okay, yeah, this would be the minimum value itself. Because then... Wait, no. No, it doesn't make sense. Oh, yeah. The sum would be the minimum value itself. Then the array value would be the thing that makes it into this. So the array value would be this, and the sum would just be the minimum itself. Okay. God, I'm so confused right now. But I guess that makes sense. That would make the answer off by 4. This would make the answer 2, or not. How is happening right now? So here we have something's like up. Something's up and something's down, like at the same time. And that's not good. Wait, where am I getting 3 from? I'm printing SI and then AI. How am I even changing this? I don't understand. Wait, so we're printing the value of S. Okay, so the value of S is changing somehow. How am I changing that? Oh wait, no, okay, never mind. These are the parents. That's fine. Somehow this is changing, and it's changing like badly. So somehow like 2 minus 1 is equal to 3 or something. I guess that's what's happening. I'm not really sure how. So we have this tree that's like, okay, we have 1. We have so this has 1 as its parent. This has 2 as its parent. This has 3 as its parent. We have some other thing that has 1 as its parent, I suppose. And then we have these values, so we have 1, -1, 2, -1, -1. So we're getting that 2 minus 2 is equal to 3. I guess that's the way this works. Oh, maybe we have to do this first? Will that work? I guess it would, right? Okay, yeah, we have to do this first, I guess, because otherwise these values are going to be -1. This is so scuffed. But yeah, these values are going to be -1, so I suppose we do it like this. And then we engineer it to pass samples and get wrong answer later. That's generally how this will work. Can't type. Okay, this is 1. Even though this value of S is like literally -1. So what's happening? Alright, no, it's not. It's not -1. Maybe it's if AI is less than 0. That makes sense, actually. Yeah, the sums would never have to be negative. That doesn't make sense. I want to check if the array values themselves are. Okay, submit. Submit first, think later. Actually, wait, let me just review this. Read into N, like do the parent stuff, check the array values, stuff and stuff. The DFS, compute this S value, then look at the children, then like add the answer and stuff. Works, right? Pray it does. Whoa, second thread in the chat. Good morning. It is actually morning for me, so I can say that. Yeah. Let's see. What else have I missed? I should learn Vim. I mean, I can't, like, the bottleneck is my typing speed, and the problem is that, like, the thing that I'm screwing up is the typing speed thing. Like, making a bunch of typos and having to retrace, like, every line and stuff. This is not exactly perfect. I don't know, maybe I can try out Vim later. But yeah, Codeforce's submission window also has its, like, it has its appeals for sure. Like, look at this. It even, like, gives you an IDE, doesn't it? Something like... has better syntax hiding than Notepad++. And, like, auto indent, you know, it's, like, perfect. Stream of me watching second thread watching me. Yeah, I could do that too. Okay. I guess this is going to take a while to judge, so I'll just move on to the next one. Oh, there it is. Well, so far it seems to be passing the samples. That's perfect. Yeah, okay. It's going to take a while. I'll read the next one. Just realized I, like, forgot to update this. Whoops. It's fine. It wasn't that long, I guess. So this one I'm pretty sure is, like, harder. Yeah, this one is much harder, like, than the other ones so far. I will say. So it's fine if you didn't solve this, because, like, this actually took me a while to figure out when I was, like, looking at it before. I'm gonna pin that. Yeah. Are we done yet? Alright, we got it. Cool. So, leave it like that. Alright, I know this problem, but I'm still gonna read it out. After the piece of a devilish mirror hit the K's eye, he's no longer interested in the beauty of the roses. Now he likes to watch snowflakes. Okay. Because mirrors, sure. Once upon a time, he found a huge snowflake that has the form of a tree. Great. Consisting of end nodes. The root of tree has index 1. K is very interested in the structure of this tree. After doing some research, he formed Q queries that he's interested in. The ith query asks to find a centroid of the subtree of the node Vi. Your goal is to answer all queries. The subtree of a node is a part of tree consisting of its node and all its descendants, direct or not. In other words, subtree of node V is formed by nodes U such that node V is present on the path from U to root. Yeah, basically it's like normal subtree stuff. Like this, the subtree of this vertex would be this, for example. Just everything that's like, everything that this is a parent of, or an ancestor. A centroid of a tree, this is a new topic, is a node such that when we erase it from a tree, the maximum size of the connected component will be at most 2 times larger, or at least 2 times smaller than the size of the original tree. Okay, first of all, like, this always exists because you can just prove it. And in fact, I have this tutorial on centroid decomposition that goes into a bunch of things about centroids. So, you know, if you want to watch that, you could. It's a possibility. But you don't have to. I'll rehash it here. So first of all, the centroid always exists. We can prove it. Second, the algorithm for finding a centroid is as follows. Actually, wait. This is like a very bad example. So let's do something like... something like this. Right. So we go here. So we start here. And we ask, is this a centroid? And basically the criterion for being a centroid is essentially all of the subtrees that we have. Let K equals floor n over 2. We can always achieve this. Then all of the subtrees must be of size at most k. So less than or equal to k, less than or equal to k. In this case, in this tree, it's going to be 4, and this subtree is of size 5, so that's not possible. So what we do is, we know that we have a subtree that's bigger than this, which means if we go into any other subtree, then like we're going to have this subtree plus this node, and that's going to make it worse, so it's going to be bigger. So that's like a problem. We can't do that. The only subtree that the centroid could possibly be in is the one that's too big. It's not centroid decomposition. I know. I'm just saying that video has stuff about centroids. So now we're looking at this vertex. And so we have some sort of residue stuff on the parents, and we check these subtrees again, and we indeed find out that this is at most n/2. So it's like, it's good. But that's the standard algorithm for finding a centroid. The problem is it may not work for this, because it could take at most O of n, or O of the size of the tree, which could be too much. But we can use the idea to sort of help us in this problem where we're trying to find the centroid of every subtree. Like basically we have to find the centroid of every subtree no matter what, because we can just have q equals n and have all of the queries be for every vertex. So instead of answering queries, let's just find the centroid for every subtree and just sort of be done from there. That's equivalent, right? Yeah. Also, there could be multiple centroids. It doesn't really matter. But the idea is we're going to do some sort of DFS. No, well, it's like weird. So say we know the answer for this. Then the basic idea is now we're trying to figure out here. If this is not a centroid itself, then we know the centroid must be in one of its subtrees. And specifically, it must be in the subtree that's like too big. So, well, the thing to check would be that like we know the answer of the centroid for this one. Specifically, it's this one. So when we go from this subtree to this one, what happens? The thing that happens is we get more nodes on the top, which means that like if this is a centroid, that means that none of these nodes are eligible. And if we have more nodes on the top, then that means that these nodes will still not be eligible. And we also know that all of these other nodes are not eligible, because like we have more stuff on the top. So whatever this subtree is, where it's like sort of whatever the remaining subtree is when we remove this, it's going to be bigger because we just put more stuff in this component. So it's never going to work since we did that. What I'm saying is any centroid that was previously invalid will stay invalid. That's my claim, I suppose. Which means that like this may also become invalid. Or actually, no, that's wrong. Not all centroids that were invalid will stay invalid. But sort of like this centroid is a centroid because it balances the subtrees. But now we have sort of more stuff on top. So the sort of like how does this answer help us with finding the new answer? And the answer to that question is, my claim is that the new centroid has to be an ancestor of this one. Let's say it isn't. Then either it's some child of this, or it like goes up and then down into some other path. But if it were to go down, then like if it were to go down, then we can sort of prove this right here. If it were to go down, then this thing itself would be a subtree. And because it goes down, sort of like this path, this is going to get so messy. Okay, wait. Let's say the subtree isn't an ancestor of this, so it's something like this, or the centroid. Then this path is going to exist. The path from this node to the new node we just stuck on. This path is going to exist and not be blocked off by this. Which means this subtree, and that's true because it's specifically not an ancestor. So this subtree, that was initially too big in the red subtree to be a centroid, is now going to additionally have this part. Which means that it's still going to be too big. So for any candidate centroid that isn't an ancestor of the previous centroid, it's going to be invalid. Which means that the only things we have to check are the ancestors of the previous answer of like the biggest subtree. That's sort of weirdly explained. But like again, we start here. We know the centroid has to be in this subtree, and therefore we can consider the answer that we got for this subtree to sort of figure it out. And we know this has to be here because this subtree is too big, so we have to cut that up somehow. So, yeah, either it's going to be an ancestor or the original answer. Yes, we're trying to find the centroid of every subtree, because then we can answer queries, like we can answer all of them. Yeah, and we're going from the bottom to the top. So, doing this algorithm is fine. The question is, what's its complexity? That would be the question. Like, it's got to be some sort of log or log squared, but like, I don't know how to prove that. So, no, this definitely isn't O of n squared. It's better than that. Like, not the brute force algorithm, the algorithm of taking the previous answer and building off that. Okay, how do you figure this out? What is complexity? So, say we're here, and we're sort of like coalescing the answers of all of these into one thing. And we sort of only inherit one of them. Which means that, like, is it O of n? Could it be O of n? Not entirely sure. Yeah, I just happened to draw a binary tree, but it's not necessarily that. Okay, so Aaron, basically the idea is we want to find the answer of this, and we know the answers for these two. So, like, we find the biggest subtree. If this subtree is greater than size k, then we know the previous centroid has to be in this subtree. So now we're figuring out, in this subtree, what's the centroid for this whole thing? I mean, it doesn't necessarily have to be in this subtree. It has to be... Actually, yeah, it does. Either this is the centroid or this subtree has the centroid. But then what I'm saying is the answer for this whole subtree, if this subtree is too big, then the centroid is going to be a parent or an ancestor of the original centroid of this subtree. And you can prove that by sort of like saying you have extra stuff up top, and anything that's not an ancestor will contain both this subtree that was originally too big and this extra stuff you just added. And therefore that makes it so this subtree is still going to be too big if it's not an ancestor. So the only possible candidates are ancestors of the original centroid, of the previous one. What do you mean split off a third time? No, you can't go back up. Yeah, the root has 3 children, sure. But it can't split off a third time. Like, it has to, it's either the root or it has to be in the biggest subtree. That's just how centroids work. Yeah, but it doesn't matter which subtree it's in. The point is it's only in one of the subtrees. And then, like, everything else is sort of, everything that's not in that subtree is sort of being added onto this. So even if we have more subtrees over here, it's going to be the same argument. Like so. Okay, I'm gonna just, I don't know how to answer this. Because, like, for every node, we take out most one answer from the children. How would you prove this complexity, then? I'm gonna just write the code, see how fast it runs, and we'll take it from there. Like, I know it's definitely not O of n squared. It's, like, either O of n or, like, n log n or something. Just a bunch of question marks. Like, it's definitely passable, I'm pretty sure. So for now, I'll just, like, do the problem. Yeah, it feels like O of n, because it's sort of like, you sort of like, for each vertex, you sort of only take, like, one of the children. And so it's sort of, maybe it, like, amortizes to only a single path that goes up the tree, and therefore the answer is, like, the depth or something? I don't know entirely. Vector, long. Wait, does it only move once? That would be cool if it did. I'm not sure. Let's see, vector LL children. I'm gonna slowly decrease the length of these variable names as we get more comfortable with this. So, okay, now we compute all the answers, and then LL centroid. Actually, I'll call it children again, why not? So for each CN2 B, looks like there's 0 indexing, so children p dot push back I plus 1. Then we sort of like, okay, void DFS, cur LL parent. Then, like, what are we doing here? We got to do a sort of thing where we, like, yeah, like, this complexity is very sketchy. I'm not really sure what to do about it. So we sort of do a thing where it's like, alright, so if, first base case, if children cur dot size is equal to Actually, we can say if this is a centroid, wait. Okay, so let's do sizes. So size cur is equal to 1 for LLX child children cur DFS child cur size cur plus equals size child. Isn't it O of n because you must move the node from the biggest subtree? Yeah, I feel like it. Like at the same time, like it's sort of like the subtrees kind of switch over time. So you could do like a lot of work for one and then do that same amount of work for another or something. Well, you don't have to try all the ancestors. You can sort of stop when you find any centroid. That's the thing. I think stopping when you find a centroid would make it O of n or something. I want to see the editorial for this afterwards. I want to see how they prove it. But maybe like you can show that for a thing with this, for like a subtree with depth D, for example, then like maybe it only does O of D work or something, and then you can sort of like generalize that to the whole tree. It's sort of the work is the maximum over the subtrees, but it's like at the same time it's like not. So it's like weird. I don't know. It feels like O of n. It could at the same time feel like O of n log n. It's definitely passable though. It's definitely a complexity that will pass the problem. Is it a holiday? Yeah, it is. In fact, it's like Thanksgiving for basically like the rest of the week. So there's more stuff coming up. Like the 5K special, for example. That's like Friday or something. I'll say more about that later. What do we have to do? Okay, so LL worst equals 0. For LL child, children, cur, worst equals max, worst size child. Yeah, I mean, there's technically still school today, but like nobody goes to that. It's not a big deal. It's like an unofficial thing that like doesn't matter. LL requirement equals size cur over 2. If worst is less than or equal to requirement, then all of the subtrees are fine. So this is a centroid. Centroid cur is equal to itself, and therefore we're done. Otherwise, we have to inherit the centroid from the children. So what we can do is we can look at the children again, and then if the size of the child is equal to the worst, note that this size is going to be unique, because if there are multiple, then that means there are two subtrees with the same size, and therefore they must both be like small enough to make this work. That's just sort of how it's going to work. Like, we technically don't have Wednesday off. It's sort of like, it's a weird unofficial day that doesn't matter. Normally we would get a half day on Wednesdays. But this is a sort of weird thing that nobody goes to. So it's basically like having a day off. So cur equals centroid cur. While 1. So basically we say check the condition for a actually what may be smart is storing these for each vertex so that we don't have to recompute it every time. So worst cur is equal to 0. Worst cur equals max worst cur worst child. Yeah, that makes more sense. So if worst cur is less than or equal to rec, then yo, Demoralizer, how you doing? Special thing, it's just like a weird thing that my school does and like nobody else does this, yeah. It's like a virtual check-in, as Aaron called it. So LL size is equal to LL above is equal to like, it's the size of the current minus the size of that subtree, targ, minus 1 because the target is a value itself. Then LL below equals worst targ. If maximum of above and below, that is the largest subtree that will be split when we remove this node, is less than or equal to requirement, then break. Otherwise, we can sort of like do the parent par of I plus 1 is equal to p. Otherwise, we continue, and so we have to check the parent, so we set target equal to its parent. Then centroid cur equals targ. And actually, this is wrong. This should be the centroid of the child, the largest child. So that's basically the idea. We sort of like mooch off of the last answer, and we check every ancestor of the previous centroid until something works. Then that's basically it. That sounds right. What? Pointer and oh, oops. And target equals right. Call that P, I guess. And then set that, and then okay. This is what I get for using dumb variable names everywhere. See if this works for the sample. 1, 2, 3. Okay, what? If worst occur, I don't understand. How am I screwing up DFS like this? This is quite dumb. 63rd line. Oh yeah, this should be size. My bad. True. Okay. That is a thing. 3, 2, 3, 5. 5 also works. Okay, that's fine then. Yeah, okay. I probably would have noticed that worst, all the values for worst was 0 anyway. Wait, line 69. I have update worst cur. I wouldn't have to necessarily. Like the worst is just the biggest subtree of this node. Seems like it works. Is this page going to load? Or will it refuse to? I guess it's going to take a while. Well, we can look for other bugs, I suppose, and then we can try and figure out this complexity. So the size of the current is 1. The worst is 0. Like for each child, DFS, add the size, take the worst, find the requirement. if this is a centroid itself. Otherwise, it has to be of the biggest subtree. So look at that subtree, find the centroid of there, check the ancestors, and just do it. This is guaranteed to finish because there's guaranteed to be a centroid. Maybe it'll fail for larger tests. Read into N to Q for each value, like read in the parents, do the DFS, and just answer queries like so. Okay, I guess we will wait, because why not? Okay. So that is D. Let's see. Alright, first I'm going to grab some more water, so I'll be right back in a second. Alright, let's see. Yeah, why didn't I check the parent? Because I specifically have only the children. Still in queue, okay. Yeah, I have the water bottle. Like, I need to prepare for the children. Or what? No, I need to prepare for the problems, not the I don't even know what the children would be. Getting sidetracked. Oh, hi Neil. You say the biggest child because you draw out the pads, they form a bunch of disjoint pads. Ah, that makes sense. Okay, because then you can like here, I'll give you my status. Okay, wait, let me see if there's a link that works for that. Does this work? Like this works normally, but I don't think it'll work here. No, it wouldn't. Okay. I think you can do to see my submissions, you can go in status and then like put my name in, for example. And do it like that. Okay. So basically what Neil is saying, and that's pretty smart. smart way to think about it is like, it's something like, when you consider each centroid, it's sort of like the sort of nodes that it's the answer for. Actually, wait. How to describe this visually? Like, sort of, when this is a centroid, it's going to sort of move up and keep being the answer until a certain point. But the idea is, like, the answer for this is never going to inherit from multiple subtrees. It's only going to be the first one. So basically, what that means is every centroid, as it goes up the tree, its sort of progression of being the answer is going to form a path in the tree. And none of these paths are going to intersect. So what that means is that, like, something like, actually, wait. Yeah, it'd be something like this. And none of these paths are ever going to intersect, because that would mean that, like, both of these would somehow have to be the answer for this. But that's not possible, because we can't have multiple centroids. So all of these paths are going to be disjoint, and the complexity is going to be the sum of the lengths of these paths, which is exactly equal, or very, like, it's the number of vertices in the tree, sort of. I don't think this is ever an answer, actually. And so the number of vertices in the tree is just O of n, so the whole thing is like that, I guess. That's pretty smart. Wait, that also doesn't work? Oh, we get wrong answer. Nice, but that also doesn't work? What happens there? Oh, wait, like, see the code itself? I think I can, can I make that happen? I think I can, actually. I can do that and then show complete. Okay, you should be able to see it now, I think. See if that works. Alright, well now we gotta debug this, which is fun. So I guess let's see. Are we doing all this stuff right? Do we have enough nodes? Do we have everything? We define the sizes, we add that over the children, we define the worst, and we check that over the children. Should be enough, right? Then we, let's see, DFS, do some stuff. The requirement is the floor, I'm pretty sure. Requirement would be the floor because... No, I have a single 2500, that's it. I don't have a 2700. So if this is a centroid itself, then it would just say it's a centroid and be done. And that would be enough. Otherwise, it's in some child, and specifically it's in the child with the biggest subtree. So if that child is that, then now check that. We set the target to the centroid. Okay, then we sort of consider it like this. I'm going to reuse the same diagram over and over again. So we're solving for this whole subtree. And we're checking for this vertex. It's a different tree queries. No, it's not the hard tree queries. There are like a million problems called tree queries. So we're like looking for this vertex, and I erased this dot. That's sad. We're looking for this vertex. So like the stuff we're looking at is this, which is to say everything that's not part of this subtree. So it would be the size of this, the current vertex, minus the size of the thing we're trying to solve for, and then minus 1 Wait, no. Oh, okay, this -1 is the problem. Because I'm over subtracting this vertex. That's dumb. Yeah. Okay, that makes sense. I'm over subtracting this vertex because what I was doing the -1 for is like I'm subtracting out this subtree to figure out what this is, but like I was also thinking that removing this is sort of subtracting 1 at the same time, but that makes it wrong. It's not. It's like it's over subtracting that. So you don't want to do the -1. Is everything else right? So below is just the biggest subtree of that. If the maximum of the two is not too big, then we're fine. And do the center. Yeah, okay. That was a small, dumb mistake. Wait, this shouldn't be the size of the current. It should be the worst subtree, like the largest subtree of any child. Wow, we have a lot of people in this chat. Anna knows that too. Welcome all, I suppose. I'll try and be as good of a host as I can, although I can't guarantee that. Maybe a wrong answer on test 35 or something dumb. Or it was just slow. Okay, so we have 4 problems now. That is a surprisingly high time complexity. Or, I mean, runtime. Well, I guess that's something like input, maybe? It's not that big a deal. Are there other Davids on Codeforces? Wait. Okay. Can someone who's not in coach mode try and tell me if you can view the submissions now? I thought I set the settings so that like I have this now. Allow view other submissions to anyone. So it should work. Could someone try that just to make sure? You still can't? What? It just like doesn't let you click on it? So I have it so can no register view the code. Is there anything else I have to do? Wait, you can't see mine? Oh wait, okay. It's cause I think it's because I'm acting as a manager or something. Is there wait? There should be some way for me to like not do that. Okay, I can disable that, and I think I won't be able to see my own submissions actually. Yeah. Okay. Wait. Here's my plan. So I'll get out of manager mode, and therefore, I'll just casually exclude the wrong answer. And then I'll get out of manager mode, and then I'll resubmit all of these. And then I think that should work. Okay, cool. I'll stay out of manager mode then, so you can see the other ones too. That is kind of annoying, but whatever. Okay, so now it actually says I've solved these, which is nice. Yeah, I'm so good. I got 4 problems in under a minute. Nice. Alright, so I can get rid of all this now. This is all for 1 problem. So now I'll do the pin again. Sort of redundant, but like I don't see a better way to do it, so I guess it's fine. Alright, this one I picked because it's educational. It's not that cool of a problem, but like it's a new thing we can go over. So you're given a tree consisting exactly of n vertices. A tree is a connected, undirected graph with n-1 edges. So again, we have both of the definitions already, which is cool. Each vertex v has a value av assigned to it. Let the distance be the distance, between vertices x and y. The distance between the vertices is the number of edges on the simple path between them. So the distance from a vertex to itself is 0. Let's define the cost of the tree as the following value. Firstly, fix some vertex. Then the cost of the tree is the sum of the distances times ai. Your task is to calculate the maximum possible cost. All right. So n is big, but let's say it wasn't big. How would we even figure this out for a single one? Well, actually, for a single vertex, it'd be easy. We just check everything. So that wouldn't be nice. What we kind of want to do is something else. What we want to do is we want to do it in a sort of way that will let us sort of change it. Or we want to do all of the roots at once. Okay. I should figure out a good way to explain this before jumping into it. So let's consider some large tree. Large being largely drawn and not actually large in terms of being a tree, I guess. So we're going to do this thing called rerouting. And what that is basically, here's how this works. So this may actually be easier to explain thinking of it this way, instead of trying to go bottom up with the explanation. So say we have the answer for this. We know this quantity for this vertex. And then we want to figure out the quantity for some other vertex. Because it's sort of convenient, let's try and figure it out for a neighboring vertex. So say we move from here to here. Then what happens? So everything in this subtree gets one farther away. And everything in this subtree gets one closer to our current vertex. Specifically, the movement would be from here to here. And sort of this is true for any vertex. So there's some section of the tree, specifically everything on one side of the edge will get farther away from our current vertex, and everything on the other side of the edge will get closer to that current vertex. So since we already know the cost for this, we're interested in how much the cost changes. And the change is, so we add, all of these distances get added by 1, which means we add the sum of the AI in this green subtree. And then here all of these distances are closer by 1, so we would end up subtracting the sum of the AI in this subtree. Right? So that's sort of it. Now all we need to do is figure out the sum of AI in each of the subtrees. And well, sort of the way this works is we know the total sum of the AI. Let's call this big sum, and therefore I'm going to draw it huge. Let's call this big sum. It's an ugly A. Right? And then if we can figure out this one, which is sort of just the subtree sum, then we can figure out the rest of it in quickly. Because it's just this huge, massive, big subtree sum, the sum of the whole tree minus the sum of the subtree. That's everything else. Alright, that's one way to do it. And in fact, I'm going to implement this because it's going to be the easiest way to do this problem. But there's another way that's explicitly more sort of generalizable that I'll also go over. Yeah, okay. Let's just first do this simple solution. So we ask for each thing. By the way, this shows it's a very distinct difference between a div 3 1900 and something else 1900. So read into n. Then 2 times 10 to the 5th. Okay. Still can't type. I should stop trying to type fast because it's just going to make me make mistakes. Yeah, I sort of handpick problems to sort of have things like this. It was less random than last time. So the maximum possible cost of the tree, right? So we ask. So some so it's sort of like this, and then we say so this sort of first DFS we do is just to figure out the cost for the initial node, which is just like AI times like the sum of the depths. Yeah, I did have to like mind solve all of them, unfortunately. The best thing to do is to have someone else do it, I guess. But I was like kind of like lazy. So I'll probably that'll be what happens next time. I'll have someone else like pick some stuff that sort of represents the sort of things I want to cover, and then I won't know them, someone else will, but it'll still like work, I think. But yeah, for this time I sort of had to like actually solve most of these. Except for the last one. The last one I don't know. The last one I'm figuring out right now. So we gotta like, now we do the DFS, like the normal DFS. Ants equals max ants cost. Oh, and also this should be 0. So now we do this like this. So we figure out the answer first, and then we say, so how much does this change when we go down from here to here? Well, we have this original cost. The vertex we're going into has everything that's getting closer. So first, let's look at the vertex. Next is not equal to parent. Then sum child is equal to just like the sum of the next. And then the sum of the current, this green thing, is going to be tot minus that. Then cost plus equals, so we subtract sum child. and then we add some cur. Then we DFS from that one. Next cur. And then we sort of undo this because now we're sort of moving the root back up here. And now we're going to start solving for other subtrees. So we're solving for each root by sort of figuring out how to move the root down one vertex and then undoing it so we go back up. So we move the root here and then we figure out the updated cost. We move the root here, we figure out the cost. Then we move the root back up and then we solve for this subtree. And then we go here and then we move back up. We go here, we move back up, we move back up again, we move back up again, and then we do the same thing for this subtree. And we can move the root one vertex by just using this formula. But by doing this, like we can solve for all vertices at once using only single edge sort of movement things. And so the movement for a single edge is just figuring out how the costs work. Then we do cost minus equals this quantity, and then we start solving for other children. So this in general is called rerouting. It's just like cool. Because it's like, if you think of this like a dynamic programming thing, where you let dpi be the answer for subtree I. Like so. Handwriting is slowing me down. If you think of it like that, then it's sort of like, okay, there's no way I can, wait up, hang on. I have to figure out a way to make this not messy, ideally. Can I undo all of these? Damn, I can undo, it lets me undo everything except for the first one. That's so annoying. Okay, but if you let dpi be the answer for the subtree I, then like when you go from this to this, the cool thing is that like this dp value and this dp value are the only ones that changes. Because everything else is relative to the root, but in terms of like all of these and all of these, the root sort of like stays the same essentially. So the only dp values that are going to change are the two ones that are on the edge that you're moving the root from. So therefore it's sort of just like recomputing the dp only for those. And so more generally, applying to more things than this, you can find some sort of like subtree dp for all vertices using this rerouting trick. Jesus. Okay. Choking part 2. But yeah, this sort of like generalizes. And that's why it's cool. That's why I put this problem on. Because it's sort of tree DP, but it's like even more than that. Okay, somehow it's wrong. Do we get this one right at least? Yeah, I did pre-calculate the costs. Okay. Let's figure out what's happening then. Wow. I've done this before. First stream. Okay, so 0 is 47, which does not make sense at all. And we say 3 is 133. What exactly is happening? Alright, so first of all, this should not be 47. Oh, wait, should it? So it's 17, 21, 17, 21, then 13. I guess that makes sense. Okay, 47's right. Then when we go into 2, is it just coincidence that I happen to be visiting the vertices in order? That's kind of cool. So when we like go into this one, this cost should be so it should be 10 plus, let's see, these are both at distance 2, so it should be 54, and then these are all at distance 3, so it should be 90. and it is 90. And then we go down here, and this sort of like screws with everything. And then this sort of adds all of this. Okay, let me explicitly, like, okay, I mean, I trust them to do it right, so I'm not exactly sure what's happening. Somehow this whole thing gets screwed up. Oh, it's because I don't even have sum. Wow, wow. Yeah, I'm not even doing that. That is stupid. Yeah, I didn't even do that. That's oh, why? Okay. Yeah, I should probably like compute the array that I'm using. I'm pretty sure that would fix it. Yeah, 121. Okay. That was dumb. Did I do any other dumb things? So, C into N, read in like the values, read in the tree, you know, do some stuff, don't be stupid. Read in the total, compute the cost, at the same time compute the sum. So do like the cost and then initialize the sum to be that. And then like the answer, find the changes, read DFS, do everything. What reveal? What reveal do you mean? Oh, like Friday. It's not exactly a reveal. It's like a different type of thing. But it's gonna be Friday. It's scary that it's hanging. Okay, cool. I'm not sure why that takes so long either. Isn't it like 2e5 or something? Face reveal? Not yet. Can't do that yet. That's not how that works. I told you 10,000. That's what's happening. You people know this already. I know you guys do. You definitely know this. Just messing with me. 10,000 subscribers is the 10,000 subscribers is when it's happening. So if you haven't subscribed but you want to see a face reveal, then you know what to do. That's my pitch. I did do a keyboard reveal. I have this other video. I have this other video if it'll open the link. I call it a desk reveal. And basically, like, it is what it is. It's a desk reveal. And then inside it, you can even see my hand, so it's, like, perfect. I'll do a keyboard camera once I, like, figure out how to not have a terrible camera. Because I don't have a like, my current camera is either, like, my phone camera or my laptop camera, and neither of those are, like, good to set up. So I'm not sure. But anyway, yeah, this problem is rerouting. It's, like, cool. There are more problems that use it. I probably should have included them, but I didn't, so I guess you can find them on your own, or maybe I can link more problems later on. Stuff that maybe won't be in the mashup, but just like will exist. I don't know why people are so eager for this. It's like bewildering. Yeah, tree painting, that works too. Okay, this is called tree queries. You are given a rooted tree consisting of n vertices numbered from 1 to n. The root of the tree is a vertex number 1. A tree is a connected undirected graph with n-1 edges. You're given m queries. The ith query consists of the set of ki distinct vertices, v1i, v2i, up to vi ki, or vi1, vi2, up to vi ki. Your task is to say, if there is a path from the root to some vertex u, such that each of the given k vertices either belongs to this path or has the distance 1 to some vertex of this path. I did forget to change the pin, that's true. Thank you for that. I mean, Next time is going to depend on the vote. That's basically how it works. I'm always just going with whatever people vote on. So if you vote for probability and combinatorics, that's what I'll do. Okay, I'm trying to remember. There's like a smooth way to do this. I don't remember my original solution because I solved this in contest. And oh yeah, I remember how to do this. Okay. But that's like, let's not do that instead. Let's do something better. So I'm gonna do the overkill way. Look, so basically here's how this works. You have a tree again, as always. We're always given trees. It's just how this mashup works. In fact, it just says you have a tree, right? You're given a rooted tree and vertices 1 to n and minus 1 edges. Or just, yeah, etc. In fact, they define it, which is nice. Some problems make you figure out that you have a tree, which is a philosophical design choice, I suppose. So you're given a bunch of vertices on a tree, and you essentially want to figure out, does there exist a path from the root to some other vertex, such that every vertex in a query is either on this path or one vertex away from some vertex on this path. Okay, right? So you want to figure out if there exists some path. So the first thing to note is that, like, the path must reach the deepest node. Like, on the way of reaching the deepest node, it might reach some other nodes, but it must reach the deepest node. So, that's like sort of a requirement. Or, like, it doesn't necessarily have to reach the deepest node, but it must at least be one above the deepest node. Or it might go through, I guess, yeah. But the point is, the deepest node has to be part on the path. And, like, the path is sort of, like, uniquely determined by some deepest node, because maybe the path can go to here, but then, like, if there's more stuff below it, then the path will be determined by the stuff below it instead of this, like, thing itself. But the main observation is that this path must contain the deepest node. So first, let's find the deepest node. You can do that just by looking for depths. Like, you can pre-compute depths of the tree, that's fine. And then you want to ask, basically, consider the path from the root to the deepest node now. You want to ask, is the condition satisfied for this path? So, like, how do we do this? Well, we just need to check all vertices if either it's on the path or its parent is on the path. And the reason I'm allowed to do parent is because, say it would visit some sort of things like this, but because the path comes from the root, then it would, like, go through that vertex anyway. So we only have to check for parents. We don't have to check for all neighbors. And that makes it kind of easier. So how do we check if something's on the path? Well, it has to be between this node, the deepest node, and the root. And so one way to check that is to simply ask, actually, the definition of the set of nodes Like the definition of an ancestor of a vertex is the set of nodes on the path from this vertex to the root. Like that's the definition. So we just need to ask, is either this vertex is an ancestor of this one, or its parent is an ancestor. And this is going to take O of something for each query node, and the sum of query nodes is like 2 times 10 to the 5th. So we just need to figure out how to do this. How to ask, we just need to define some function, like is A an ancestor of B? There are many ways to do this. And, well, that's the final part of the problem. However, one trick you can do is first, to solve the initial problem, replace everything with its parent. Because if this node is on the path, then its parent will also be on the path. So, actually, you really only need to check parents. So basically ask, for this, is its parent, unless it's the root, in which case, then, like, whatever. Is its parent on the path? How do we do this? Again, we need to find this, we need to compute this magic ancestor function somehow. One way to do this is to say that, for example, actually, okay. It's like not easy to do this kind of. One way is to use this magic thing called LCA. Okay. Now, like, this is like a scary word. What it means is finding the LCA between two vertices is asking for their lowest common ancestor. That is, for two vertices, what's the lowest vertex such that it's an ancestor of both of them? Right? So, like, if we could figure this out, then this would be great. Because if some vertex is an ancestor of another, then the LCA of the two vertices is itself. So if A is an ancestor of B, then that implies that the LCA of A and B is equal to A. Because A is an ancestor of itself, obviously, and if it's an ancestor of B, then it just would be. And actually, it's not implication, it's equivalence. So if the LCA of A and B equals A, then A is its own parent, and it's the ancestor of B, so therefore so A is the ancestor of B. Okay, computing LCA is actually not really a thing I want to teach, but here, I'm going to add this in the description now. There's this cool video by Second Thread, who may or may not still be watching, and basically just like goes over a lot of tree things. So if you use this, like this video will teach you LCA basically. So you could do that. Save that there. Just get rid of the time. That's one way to do it. It's not the only way to do it. Another way to do it is to say yeah, basically you can imagine this LCA can be computed in O of log n. Then you just need to check if it's equal to the vertex. So this will give you O of log n per query node, which is in total O of n log n. But again, there's a better way to do it, so I'm not going to do it with LCA. The idea is, let me redraw this tree. It's kind of messy now. How did I do it? Like that? Yeah. To find if some vertex is an ancestor of another, it's equivalent to asking, is this vertex in the subtree of this one? The subtree being like all nodes that are under it. And so sort of like, it's equivalent to checking if it's in the subtree. How do we do something like this? Well, there's this cool thing we can do to a tree that's called either Euler-Tor or pre-auto traversal. Either one will work. But essentially the goal of this preorder traversal is to make it so every subtree corresponds to a contiguous range on some array. So like, what is this? What am I? What does that even mean? Like, if I give each node a label, for example, let me just do the preorder traversal right now. If I give each node a label, then look what happens here. So we have 1, and then we have 2, 3, 4. We'll just write them in order. 5, 6, 7, 8, 9, and 10. Now, 1, the subtree of 1 is the whole tree, so obviously that would be a range. The subtree of 2 is the values 2 to 6, which is conveniently this range. The subtree of 3 is the values 3, 4, and 5, which is conveniently this range. The subtree of 4 is this, 5 is this, 6 is this, 7 is this, 8 is this, 9 is that, and 10 is that. Look at that. Everything is contiguous. Specifically, there's some value, there's some, like for every value, there's some x, such that the subtree of this value corresponds to the range 7 to x in the array. Which also means that every value in this subtree is going to be between 7 and x. Or like the value of the index in x, I guess. Doesn't necessarily have to be 7, of course. So what we can do with this is, let's say we figured out how to make these values. Then now to check the parent, like we know that anything in this subtree has the property that its index is between 7 and x. So to just ask if if a node is in the subtree, we just check, is its index between 7 and x? And if so, it is, and if not, it isn't. So that's the idea behind it. And so the idea, the way we do this is like we just straight up, we do a normal DFS, and then we sort of give each node the lowest available position that hasn't been taken yet. And the reason this works is because when we visit this node, everything in this subtree we haven't visited yet because we're starting from the root. So its values are going to be greater than 2. But then we go down, and then we look at everything in this subtree before we go back out. And what that means is that until we visit everything in the subtree, everything we visit is going to be part of the subtree. Meaning that, like when we visit everything, it's going to just, it's going to sort of scope out this range of the array because we're only looking at the things that are in the subtree. So it's sort of contiguous. And then when we're done with everything in the subtree, we go back out and we start looking at other things. But what I'm saying is it's going to be contiguous up until we visit everything in the subtree. So it's going to be greater than or equal to 2, and it's going to be less than or equal to 2 plus the size, like minus 1 or something, which is 6, supposedly. Whatever you need to do here to make this value 6, it's going to be less than or equal to that because we're visiting everything right after. That's the whole point. So basically this shows that there's some ordering where there's some starting point, and then everything in that subtree is between that starting point and some other ending point. So finding this starting point and this ending point for each node will allow us to answer these queries very efficiently. We just need to check if the index is between this. So that's it. Find the deepest node, then ask if everything or its parent is an ancestor of this. And to do that, we can do this sort of preorder traversal, which gives us an index for each node that satisfies this property. So let's just do that. First, read into n and m. this is 285. Now, let's see. Basically, we're going to compute the starting and the ending positions. We also need the depth, so we can find the deepest vertex. And all of this we can do with like a single DFS. And we can do this with sort of like a time thing, where we like every time we visit a new vertex, we increment some sort of global timer, and that way the vertices we visit will like sort of be their indexes will be based on the time that we visit them, which is what we want. It'll work that way. DFS from the root, -1, over 0, its parent is -1, and its depth is 0. Alright, first, so start cur is equal to increment the timer. And at the end, we would set the ending position to the time. And then for each child, if next is not equal to the parent, then DFS, next, current, depth +1 because it's deeper. Then we do it like so. Now for each query, sort of like a vector, I guess. Soon to K. Actually, I can make this here. Actually, I can just make an array. Doesn't really matter how I do it. Cn to vowels j. Vowel 0. This is, we just find the lowest vertex right now. If depth vowels j is less than depth of lowest, or greater than the depth of the lowest, then like set the lowest to that value. I'm also a big fan of second thread. Alright, now we just need to check possible equals 1 for each vertex equals vowels j. If it's not the root, then set it to its parent. Because if its parent is part of the path, that also implies that the node itself will be part of the path. Just because, like, if it's already on the path, then its parent will also be. And if its parent is on the... Actually, yeah, if it's already on the path, then its parent will also be. So if its parent is on the path, that's enough. And if it's on the path, then its parent will be anyway, so we only need to check the parent, really. If cur is not equal to 0, so if it's not the root, then set cur equal to its parent. The way to do that is to, you can set parent cur is equal to par. So like, now we just check if, again, we have to check if this value is between the starting and ending nodes. So if start cur is less than or equal to the start of the lowest, because like the index of a value is just also its starting position. We can think of it like that. And start lowest is less than or equal to start or end cur, which is basically saying, is this between this value and this one? Then, actually, if not that, if it's not between, then it's not a parent, so possible equals 0, and therefore it's not possible. Yeah, and that would basically do it. There's no way this works first try, so see how it goes. Does not work. Okay. Interesting. Seems to like alternate. So first of all, what's the lowest? Let's think of that first. Oh wait, because I should 0 index. Okay, now we get it. So yes, 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 no, no. I trust it. I trust it indeed. Maybe I shouldn't trust it, but I do. Looks like it works. Cool. No, the ending value doesn't matter, because the starting value is going to be the index that we're interested in. So like it can be starting or ending. It actually doesn't really matter, as long as it's still part of a subtree. Alright, we have 2 problems left and some amount of time left. We can try to finish this, I suppose. Nobody has solved. Who else has solved this? Other people here to flex on me? Oh, why can't I see status? Oh, because I have it set to myself. Who else has solved this now? Ah, nice. Okay. Right. Timmy, here to flex on me once again. So, we got, let's see, I'll set the pin message as to always do this. Oh, I didn't even, I forgot to set F again. Damn. Oh, I always forget this. Sir. Indeed, I am sir. Yes. So you have a tree, numbers written on each vertex, number of vertex I is equal to AI. Let's define the function, let's note the function g of xy is the greatest common divisor of the numbers written on the vertices belonging to the simple path from vertex x to vertex y. Also, let's note dist xy is the number of vertices on the simple path between vertices x and y, including the endpoints. Distance of x and x is equal to 1 for every vertex x. Your task is to calculate the maximum value of dist xy among each pairs of vertices that gxy is greater than 1. Okay, so right, so the GCD must be greater than 1 for all pairs of vertices. Or like everything on the path. Yeah, you can do it with virtual tree, sure, but there's no reason to do that. There's no reason to, like, just don't. This is a 2000, why would you do that? Actually, is this going to be useful? How far can I erase? Epic. Okay, so I can save that tree and not have to redraw it. Right, so for a path where the GCD is greater than 1, that means that the GCD must be some value x. So what we can do is sort of, if we want the GCD to be at least x, then we can say that like the only elements that are possible to use on the paths are elements that have values that are multiples of x. So it's sort of like saying we create sort of a new tree on that, and then we wait, hang on. So it's sort of like saying we create a new tree, sort of only using the vertices that have values that are multiples of x. And then we're interested in the longest path on that tree. And if we do this for all x, then it will work. I'm pretty sure we don't have to do it for all x, but it's like, it's not that big a deal. We have 5 seconds anyway. Wait, hang on. Actually, how would this work? So if we do it like that, then like if we check it for 2 and we also check it for 4 or something, that's like totally redundant. And there's no reason to do that because any vertex that would be included for 2 is also included for 4. I mean, no, other way around. Any vertex included for 4 is also included in 2. So like the only things we need to do are basically, we only need to check primes. So for some prime x, we look at all the vertices that are multiples of that. And then we just say like, let's make a forest out of only the vertices that have multiples of x. And then we find the longest path for each. And that guarantees that the value of the GCD will be x. So, yeah, that's one way to do it. I'm going to do a lazy sieve. Okay, scene to end. Const LO max equals 25 plus 200. Something like that, I don't know. End of the 4th over 3. I don't know what. Actually, no, this is stupid. You know what? It's not stupid. Whatever. I'm writing sieve from scratch because I don't want to paste in my template. So basically, we're just using sieve to find all the primes and like do stuff with that. I equals 2. I is less than max. I plus plus. I think that's right. Because all the multiples obviously can't be primes because they're multiples of a number. So we just sort of like think of it like that. What did I do? Yeah, so it's kind of like that. And then we say, right. So now for each prime, just make sure I did that right. Something like that, right? Yeah, looks good. Okay. So now we're going to sort of create an adjacency list for every Actually, we don't necessarily have to do that. Well, yeah, actually we do. Okay, so vector pair LL. We're basically creating a list of edges for each x, and that this edge would have to include vertices that are sort of like multiples of x. Oh, how did I print a vector? I have a template thing that does that. Max. Yeah, I know, but you have to create the adjacency list beforehand, don't you? Otherwise, you like. That's true, I guess. Huh, actually, that's. I guess so. Yeah, okay. So you don't have to do it so explicitly. Sure. What I do have to do, though, is somehow figure out the values that are multiples. And to do that, first you gotta, like, read in the values. There's like a lot of separate things. A lot of things happening at once. Yeah. So first we store the list of indices that have each value. Then for each prime, ants is equal to 0. For each prime, p primes, then we find the vertices that are sort of involved. And we say for LLI equals p, I is less than max, I plus equals p. We're iterating through all the possible, like, we're iterating through all the multiples of p. Vals I ink dot push back check. I know you can do some sort of insert with iterators, but I don't really care. So then now we have a list of vertices that divide each prime. This works because each vertex divides at most log n things, or it has at most log n prime factors, so that's n log n. And at the same time, each, like, this is sort of a harmonic series. It's sort of like sieve. Its complexity is something like maybe n log n, maybe just n log n. So either way, doing this is fine. It's only going to take out most n log n. So now we have to solve for this. And then we say, we also keep a visited array that stores the latest prime in which we visited that vertex. And then if this visited array, if the value is equal to the current prime, then that means we visited it in this run, and otherwise we haven't yet. So then now we're going to, for LX included, if visited x is not equal to the current prime, that means we haven't looked at it yet. So we say, how do we do this now? So we, like, somehow we have to find the diameter. So it's like, so we create another vector, dists. And this will basically store a pair of the distance and the vertex with it. So then we can finally do this DFS. Vertex and the parent, because it's still a tree, so we can do that. And also the prime itself. Then we say, and the distance. And the distance. So let's like do some sort of, yeah. So dists.push back make pair dist cur. Then for, and also visited cur is equal to the prime. LO next edges cur. If next is not equal to the parent, the previous vertex. If the value is divisible by the prime because we're only looking at those, then DFS next current distance plus 1, and we maintain the prime. Actually, this is also saying so we kind of don't need to do that. Wait. There's something going on. Wait, why do we even need a visit array? Wait, why do we even need a visit array? It's a tree. Oh yeah, this should be equals 0. Whoops, thank you. Yeah, wait, why are you guys talking about a visit array? It's a tree. I'm confused. Is it not a tree? Like, it's a tree and then you have forests. I'm not sure what's going on in chat. I don't think you need visit at all. Actually, wait, you do need that, I guess. You need it for components. You need it for components, but you don't need it for the DFS itself. Okay, I see. I see what you mean. Yeah. Whoa. It's like a phone call. It says scam likely, so I probably won't touch it. It's a good idea. Oh, you're doing it for each vertex individually? I guess that would work. Hi. Yeah. You can do a thing. Yeah, so like something is going on where we got something. Alright, for this component, dists.clear DFS x. What are you what? No, guys. I can't I can't show you the call, but it said scam likely. I don't know what you're talking about. This is slander. Okay, wait. So here. We're looking from this vertex. Its parent is -1. Yeah, the food and purses. Sure. The distance is 0 and the prime is p. Then LO farthest far equals dists 0. if dists I dot second dot first is greater than dists far dot first, far equals I. And then we like, so ind equals dists far dot second, then dfs ind -1 0 p, and that's the diameter of this thing. Now this dot clear for pair ll x dists ants equals max ants x dot first. And that basically means for this thing, we're going to, we're doing the standard diameter algorithm, which is basically pick some arbitrary node. Then you can find the farthest node from that one, and then the farthest node from the farthest node is going to be the diameter. That's like provable. I don't want to prove it, so I won't, but basically that's the algorithm we're doing. So first, I'm finding the farthest node from the arbitrary vertex that we found. Then from there, I do another DFS from there, and then all of those are possible answers, so that's like, I just check all of them. And I build this sort of like implicit forest for each prime, everything that's a multiple of each prime. So ideally it would work. Edges. What? Do I not have edges? Wait, where? I haven't even read in the edges, nice. Vector, LL edges, 200,000, yeah. 4. Great. Doesn't even work like that. Okay. How does this work, actually? Oh, am I adding 1 to it? Okay, so this is that plus 1, I suppose. And then we explicitly include values that are 1, so I guess that would work. Or we don't include them, yeah. And then we'll try one more. 3, 1, or 2, 1, 2, 1, 2, 2, 3. Answer should be 1. Yeah, okay. Alright, I don't trust this at all, but I don't really care, so I'm just going to submit it. Probably very likely to be wrong. I guess not. Okay. Wow. So here's the idea. Again, we create a forest based on only the vertices that are multiples of x. Because if we use vertices that are multiples of x, we know the GCD will be at least x. And then, therefore, all of those vertices in that forest will be candidate like the thing. Yeah, I forgot to... Wait, I said I didn't update the pin, and then I acknowledged it, and then I forgot to update it again. How did I even do that? Let me finish this explanation. So, yeah, and then I'll do the next one. So, like, everything in this sort of implicit forest, for example, say we are interested in things that are divisible by... It doesn't even make sense. Like 2. So then we get 2 and 6. We create this forest with 4. We create something with 8 and 10. And then now we're interested in this sort of longest distance between 2 vertices in this forest. And that's essentially just like finding the diameter of each of these components, which can be done using a well-known algorithm for finding diameters. So yeah, And this works because it checks like all possible values of the GCD, or all possible values that the GCD could be divisible by. Alright, we are on to the last problem. And supposedly this one's very hard. I picked it to be like much harder than the rest. Am I the only one that solved this? Other people should do this. Okay, yeah, I'll update the thing now. So I have the rest of the stream to do this problem. Yeah, I have visited that like maintains components themselves. What pilgrimage? I'm never gonna visit that statue, you know. That's not happening. I think it's too dangerous. This problem is 2,500. So we'll see how it goes. Oh, I forgot to pin it. Okay, I'm being dumb right now. Yeah. Can mods pin messages? Or is that only a thing I can do? Yeah, it should work now. Alright, Pasha is a good student and one of Mojak's best friends. He always has a problem to think about. Today they had to talk about the following problem. We have a forest with n vertices and m edges. There are q queries we should answer. In each query, two vertices v and u are given. Let v be the set of vertices in the connected component of the graph that contains v, and u be the set of vertices in the connected component of the graph that contains u. Let's add an edge between some vertex a in the first set and b in the second set, and compute the value d of the resulting component. If the resulting component is a tree, the value d is the diameter of the component and is equal to -1 otherwise. What is the expected value of d if we choose vertices a and b from the sets uniformly at random? So again, we're back to expected value. Can you help Pasha to solve this problem? The diameter of the component is the maximum distance along some comparison. Yeah, we just did that. Among some pair of vertices in the component. The distance between two vertices is the minimum number of edges on some path between the two vertices. Note that queries do not add edges to the initial forest, otherwise it would be annoying to do. So actually this isn't, maybe this will still work, but I have to add more trees onto this now. So we have a forest, which is a bunch of separate trees. So we do this sort of thing. And we're interested in the expected value of the diameter when we essentially pick two components. Like say we pick two components. And we're interested in the expected value of the diameter that we get when we connect two random vertices by an edge. So yeah. And if the components are the same, then adding an edge will create a cycle, and therefore like the value is -1 if the two components are the same. That just means they can use random test data and have it not be like annoying. So yeah. So assume we're working with two different components, because if we're not, it's really easy. Then like what's gonna happen when we do this? We add some edge. Then there are three possibilities. Or two possibilities. Actually no, three. So first of all, the diameter could be one of the original diameters of the tree. That is, it could be, the longest path could strictly be, actually a better way to think about it is, either the diameter uses this edge or it doesn't. If it doesn't, then it's simply going to be the diameter of one of the original, like, trees. So we can explicitly check those. Actually, we can't, but either it's one of the diameters of the trees, or it uses this edge, and therefore it's the longest path from this edge, plus 1 for this edge, plus the longest path from this vertex. So it's the maximum of the maximum of the subtree sizes and the longest path from the things we pick. n to the 5th over 3? What? Okay, not this one. So basically, we're interested in the expected value of, let like S be the maximum of the two subtree sizes, which is constant. Then it's the maximum of S and 1 plus, like let DI be like the farthest distance from I. Cube root decomposition. That is pretty slightly absurd. So it's the maximum of S and oh wait, are you talking about this one or that previous one? S and 1 plus DI plus DJ for the two nodes I and J we pick. So kind of like let's split into two cases. Either this is bigger or it isn't. Right? So like how do we do? Either it's bigger or it isn't. Alright, so and again we have a bunch of queries. If this were one query, we can do some sort of two-pointers, but for this it's not exactly possible. Maybe it is some sort of decomposition. Wait, which problem are you talking about? Are you talking about the previous one, G, or this one? Okay, because I'm thinking that square root decomposition will work for this one. Here's why. I think so. Let k equals square root n, like rounded to the nearest integer or something. Then say you have some forest, say you have some big blob of forest of size greater than or equal to k. Okay, actually no. The first thing is the first thing we need to ask is, wait, it doesn't have to be cube root decomposition. You can do normal square root decomposition and be fine. The first thing to do is how to find the answer between two forests. You can do it like so. Compute so you have two forests, like arbitrarily selected. Now, initially pre-compute DI for all vertices. Then in each forest, sort of like sort the values of DI. So we have a sorted list of DI for each forest. Then fix some value of DI in the first one. Like say we have two lists, 1, 2, 4, and 5, and something like 2, 5, I don't know, 11, 29,000. And this one, handwriting is very good. Then say we fix this. Then we're interested in the values We're interested in the values that are less than s, because otherwise we'll like only have s. Solve for arbitrary k and then minimize. I'm not sure what you're doing. Look, we're interested in the values that are less than s, which means that essentially we can do this sort of 2 pointers type strategy, and we can keep track of the largest index we have such that everything's less than x. And then we just do like, it's sort of like a prefix sum of these values. I mean, it's basic 2 pointers. Then when we move this one, the pointer to the value that makes it less might move over to the right. And so we sort of just continue doing this for each of these possible values of di. And then the rest is going to be, actually maybe we're interested in the values that are greater than. Either way, it doesn't matter. The point is we can do 2 pointers. And yeah, we're interested in the values that are greater than, I suppose. Because then we're interested in the sum of those, and the rest will just be s. So this 2 pointers will take O of max of the like the size of the forests because of 2 pointers. So then, wait, I don't understand why you need a cube root. It's like, so this solving for a single pair of forests is going to be O of max of the 2 sizes. And, let's see. Actually, maybe it does require a cube root. Interesting, because the max makes it kind of hard. Interesting. How would this work? Yeah, okay, maybe that will be cube root. Let's see. There should be some better way to do it then. Because, like, the time limit's not that good. Let, note that the diameter is the maximum over all di. And yeah, I'm seeing what you mean now. Okay. So we have 2 forests, then we, like, figure something out for that. What we could possibly try to do is try and solve for a single forest, and then like let that size be k, and then try and like solve for all other forests. And naively, this would be O of k times, or be like, there are what would this complexity be? It's like not that great. Like say you have x things that are size greater than k, which means that x itself is going to be less than or equal to n over k. And it's sort of like O of x times what? Alright, let me figure this out. Let me figure something out at least. It's x times like m minus x or something. Alright, no, it's like worse than that. Okay, whatever. If you've solved this already, let me figure this out. So the diameter will be the maximum distance among some pair of vertices. Right, now somehow we like... I have a separate idea. We can also solve this problem in of like the minimum of the sizes times log n by just sort of like explaining the 2 pointers a bit more. So doing this sort of square root decomposition I was thinking about, that gives us m root n log n, which is terrible, but that's one way to do it. But perhaps there is some better way though, because like actually yeah, we can just kind of like wait, okay, never mind. These values, all right, everyone, I get it. The values are at most like the size itself. So you can like make an array where some sort of prefix sums for each thing, and then not have to binary search. I get it. Okay, fine. So that kills the log. I'm dumb, alright? You should accept this by now. So now we can solve an O of min size. Now we can do square root decomposition, right? That should be enough. No, I am though. Like I am rushing too much into this. Wait, Everroll, that works, right? Am I missing anything else? Like it just solves it in O of the minimum of the sizes? I break on stream because I'm interacting with chat. That's mostly why. I mean, okay, that's it. So like basically it's this 2 pointers idea, except we don't actually do 2 pointers. It's more like we keep a pointer on like the minimum one, and then because these values, the values in this array are at most k, then like it's basically just like accessing an array at like a certain point, and then querying the sum of all the values that are greater than something. So that will work, and then like, alright, so now we can solve an O of minimum of the sizes. And the reason this is cool is because solve for all the value. So we're going to do square root decomposition. Let k equals root n again. Yeah, I mean, it's still just prefix sums, though. It's not like that bad. I mean, most of it you like solve it for one, and then you apply that to solve it for all. That's not terrible. So let k equals root n. Then for every forest with size greater than or equal to k, pre-compute like solving it for all other forests. This will take, we have at most n over k values, which is equal to root n values, or root n forests that have that many nodes. Which means that like this is in total, it's going to take root n times n, because we can like it's the minimum, but we can engineer it so the minimum is still n. So this is n root n. I do remember you, yes. And then the other one is, so this will solve it if either of the query nodes have size greater than or equal to k. Because if so, we've already pre-computed it. But now otherwise, for the queries that we haven't computed, we have size 1 and size 2 less than k. But then size 1 and size 2, but what that implies is that the minimum of the two is less than or equal to, or less than square root n, which basically means we can compute this query in square root n. So in total, the first part is m root n, the second part is q root n, so the complexity in total is O of n plus q root n. And I think that should be good. I did say I remember you. Alright, now we just have to like figure this out. So what we need are values of D and then prefix sums on them. So the way to do this is to, why would I fake remembering you? I have no motivation to do that. I'll make this work. I'll make this work. So edges okay, now say 300 should work. This is square root n. For I equals 0, I is less than n, I plus plus. If comp I is equal to 0, do something and like make that happen. G is like the current group number, so like a global variable. And okay, so now we like let's find the values of D, define that as that, and then it's like rerouting, isn't it? Something like that. Something like rerouting. What do we even make this? So I'm just in the longest path that goes through I, which is to say, let's see. So dp is initially the deepest node from I. dp cur is equal to 0. Which is cur. If it's not the parent, then dfs next cur, then dp cur equals max dp cur, p next plus 1. Now we find the deepest node from each point. This is the first part. Now we do the second part. Actually, it's sort of like, we don't even need that. Yeah, I think multisets are a better idea anyway, because you need to find the two greatest anyway. So it's like not that, I don't know. Yeah, I think multisets are the best idea. It's kind of, yeah, it is rerouting. Although I've also done rerouting in problem, yeah, I'm saying multisets, that's like, exactly. I've also done rerouting in a separate problem, and that's much easier to understand, I believe. This will be true with maximum cost, so if you want, you can try rewinding to that. So for each thing, edge.insert dp next. Now, for the next thing, which is, first we find the answer for this. It's 1 because of itself. So its edges, so the distance from 1 to something to itself is 0. Yeah, then you can sort of find it out at the end. If edge.size is greater than 0, let me sort of do the same thing. D cur equals now for each child, if next is not equal to the parent, then val equals so edge.erase val. Let me sort of find the maximum. And then we do reroute, so we change the root from current to next, and therefore, so we say dp cur equals max, dp of next max val dp cur plus 1. then DFS2 next, current is the parent. Then we reset. Let's see. So that is basically, it's everything except for that child, which includes the parent, which should work, I suppose. Or this should be +1, actually. Yeah. It should be +1, right? And we sort of like erase val +1. This is like sketchy. Maybe it should be something like this. And the current value is the current value of DP. Except it's like bad, so what we need to do is we need to adjacent, or like erase it from the adjacent nodes so that we explicitly don't include that child. Then set it to whatever's left, if there is anything left. If so, set DP cur to that because it's everything else. Set DP next to the value. Like it considers cur as well. Then do the DFS. Set DP next to, like, just reset it basically. -1. And cur value is fine. And then here, considering the things that we could take paths from, for example, like if we have a tree like this, then we just like put all of these in a multiset and take the two biggest from all of them, and that would be the diameter. True, I would have to reinsert that. Yeah, afterwards. Okay, so anything else I'm missing? It's just resetting the DPs. Alright, let's test only that. Yeah, I forgot about that. I hate multi-sets. I usually do remember that. I don't know why I didn't this time. Okay. Let's just see if this works for like some big case. And create the case in here. So we have 18. Why not? So 1, 2, 2, 3, 3, 4, 3, 5, 2, 6, 1, 7. It's not that bad. 1, 7, 7, 8. Relax, I've been going for almost 3 hours now, or 4 hours. Right, and like label this at 11, as 12, as 13, as 14, as 15, as 16, as 17, and as 18. So then 11, 12, 11, 13. This is a very strong case, so hopefully we don't, I don't know, 17, 18. Okay, and that's 14 edges. Let's see if it even compiles. I don't have queries. Let's put a 0 there for now. Answer that later. Okay, everything's 6 somehow. Is this right? Wait, what am I even doing? Why am I doing 2? This isn't... I'm confused. Okay, I don't need that. I just need the biggest. Yeah, I just need the farthest distance from a specific node. That would make more sense. So this is 3. Let's see. Let's see if this is right. How is 0 0? What's with that? Oh, we can also max dp cur, consider it like that. Wait, why does it not consider that immediately? Zero should not. What have I done now? Somehow 0 is 0, which doesn't actually make sense. Because it only does that for like the beginning of the subtree. Like the other subtrees work, that's the thing. What have I done? Okay, so oh, and it's also something like cur is equal to g. That way you don't revisit things, I suppose. I wanted to index the groups, but it shouldn't be the... I haven't done that either. Nice. This is like exactly what happened last stream. Okay. So we have 3, 4, 5, 6, 6. 1, 2, 3, 4, 5. Let's see. So this is 4, this is 5, this is 6, this is 5. Okay. We have 1, 2, and 2, 1, 2, and 2, 1, and 1. Looks good. So I'll leave it there. Is DP also what we expect? I hope so. Just to make sure, it's 3, 2. It's basically the height, almost. Yeah, like 3, 2, 1, 0, 0, 0. 2, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. Okay, perfect. So now we get to like the fun part, of course. Let's see. So this is for each component. Then for LLX has cur. I suppose that would be how that works. db g dot push back dx. Yeah, well, pre-computation, like, all I have to do now is write the solve function, solving for 2 components, because from there it's, like, easy. But, okay, now we do, like, prefix sums or something. Actually, this should be, like, fine. We need prefix sums themselves, and we also need frequency. We might as well store diameters too. Why not? So I don't actually need this. It's more like well, diameters is just the maximum of D because we fix anything as an end and then like compute there, right? So when we do that, it's like don't need dB. This isn't a thing. What we really do is like now suppose we want suffix sums and not prefix sums. So yeah, sum G plus equals, or no, it's not G. Yeah, it's like G and then dx plus equals dx. And then freak G dx plus plus. R the same thing for this now. Freak. That gives us suffix sums. Is that enough? I feel like it should be. So now like it's pre-computation, and then from there okay. So this whole thing is now a thing of the past, assuming it works, which I can't say it will. Let's just like go over this, because it would be stupid to mess that up. So set the diameter to 0, say the diameter is the maximum of all values of D, create two vectors, the prefix sum, or like, I'm going to call it prefix sum even though it's not actually a prefix sum, and the frequency of each value. Then the prefix sum is the sum of the values themselves, and the frequency is just the number. So do suffix sums, like so, for both prefix sum and freq, and then do it like that. And then now we can use these values to solve it. How fun is that? So the way to do that is to essentially what would we say? Solve for two components, A and B, if let's see, dA is greater than dB, swap AB. So let A be the smaller one. Actually, we can say sort them by their sizes. Yeah, actually, we want to do that, not by diameter. Sizes. Do it like so. So now for each, let's see. For each possible value of the thing we can take from A, we use that exact value, I guess. We do sort of the same thing for the other one. Current frequency and then the current sum. So this is the exact value that we have here. Then the suffix is equal to, we're interested in the values that where 1 plus di plus dj is less than s, or greater than or equal to s, I guess. So we can do it like s minus current value I minus 1 and we max it with 0. Then do something like that. I gotta be so careful with doubles later on. The suffix is going to be the maximum of those two. Then we sum tot plus equals. Oh, actually, this should all be A. A. Should be A. This should be A. The frequency times the sum plus whatever. Wait, that's like not right. It's like the frequency is like out here somewhere, because that's included in every pair. And then it's like this is annoying. So we have k values of di. We need to sum up dj as well. So it's k times, I think each value is repeated k times. We have everything else that's like the sum. So it's like p sum b suff. I'm definitely going to get this wrong. Oh no, I can feel my concentration. Yeah, I'm definitely done after this problem, of course. So it's like the prefix sum of b and the suffix. So 1 plus di is fixed, actually. What we're interested in is the sums of dj, which is essentially the frequency of the current element that we're adding the first array times the suffix sum. even though I called it prefix sum. Then it's essentially C sum plus 1 times C freak times like the current frequency times the something of the other one, like freak B size. The rest is equal to has B dot size minus this frequency, and tot plus equals S, because everything else is going to be S, which means we're summing up that, and the number of values is going to be that times C freak, the current frequency, times the rest. That's everything. Then return total over has A dot size times has B dot size, because we're looking for expected value, not the sum. Everett, are you still here? Are you still here? Okay, now, yeah, unfortunately it's going to be 4 hours, which means I don't think it'll have captions after, which is kind of annoying. There's not much I can do about that, though. If, where is this? I do has I dots. So if we have this more than or equal to k nodes in the component, k being 300, so square root n. This whole thing is for square root decomposition, of course. Has I dot size greater than or equal to k, then we got to, what do we actually have to do? That would be a question. So we like pre-compute all of the stuffs. How do we pre-compute all of the stuffs? Well, we just use this function. Let's see, map ll large. Large I equals count. That way we can reverse it later when we and we also like store if everything's big, is big I is equal to 1. Then we like, wait, what the hell is that? What is that for? I don't even need that. It's literally this. So then it's just 400. Is this useful for low rated? Probably not. Like this is the hardest problem in my mashup. So pre-comp plus count. Pre-comp count j is equal to, what do I call it? Get comp ij. And if a is equal to b, return -1 as the problem defines. Actually, this should be from 1 to g. It should also be from 1 to g. Yeah, I think. Looks like it. So now we can finally do the queries. After this whole thing. Yeah, like this whole last part of the stream probably isn't going to be that helpful for most people. It's just kind of like for my own gratification. If has u.size is greater than or equal to k. Then we pre-computed it. So pre-comp large u v. Actually, just define it to be this. That way I can debug if necessary. Wait, I got rid of the if statement. And this is equal to that. Else if the other vertex, pre-comp large v u, else ants equals get comp u. Actually, yeah, I should say u equals comp u. Ideally, I will be almost done with this stream. Ideally it'll be almost done, because this is the last problem, and I'm assuming there are going to be a million bugs for this, but ideally we would be done soon. So this is simple, right? Like, do pre-computation. For each group, for each component, if it's big, like, reverse the thing, and then for each other thing, do the pre-computation. How does occur? What is cur? I'm not actually sure what cur is. Has I? What is cur? Is that like something I did? Yeah, I was also thinking of like reusing the answer somehow, but I'm not entirely sure how that would happen. Segfault? Yeah, makes sense. Okay. Where does it get to, at least? Just gonna print values until we get somewhere. So we get to the query part. Also, this should be int, otherwise it'll definitely MLE. Do we have? No. Oh, that is pretty smart. Sure. Nice. I mean, it's like this versus like not that much of a difference, so I guess that would still work, but sure. What the hell though? Maybe this is causing problems. Well, it shouldn't, because it should only be this. So get comp is the problem, I guess. Yeah, okay. So what's the problem here? Well, print the index where it dies, if it even gets there. I think printing -1 is a double is not that big a deal. So we segfault. Where are we segfaulting? Oh, okay. So I is 0. Then the frequency, do we get here? I'm not like smart enough right now to be able to look at my code and understand what's going wrong, so I'll just like, so we get 0 and 0, which makes sense because I is only 0, and there's nothing that would have distance 0. Then the suffix, oh, maybe it's like, what am I doing? Don't think it would be that, I guess. It doesn't even compile. So it gets there. What is happening? Alright, wait. Has to be endo, otherwise it won't print. How did I lose the input? Also, what is this case? Oh, it's just a single edge? Are you kidding me? I'm failing a single edge? Wait, actually, this should be, 3 1's fine. 2 3 should actually be. So we're solving for 2 and 1. Component 2, component 1. Okay. That makes sense. So this could be diam B. Wait, no, this is... It should be diam. Right. So suffix is -1. Okay. Is that what it wants? Wait, how's the diameter of B 0 also? That's like a problem. So tot plus equals C frequency plus... Oh, it should all be +1. Ah, okay, that was my mistake. I thought I was doing +1, it wasn't. Alright, now it gets 0 as an answer, which is not good, but at least it's not crashing. So we have suffix. This, I do not understand why it's not getting anything for these. So like... Interesting. So 0 and 0. Why would it be that? Yeah, the prefix one makes sense, but the frequency like doesn't. Oh, this should be diam itself and not -1. Maybe that would do it. Huh, okay. Does it work on the other sample? It does not. That's sad. I don't understand how the frequencies are still 0. This one doesn't make any sense. What the hell? How is the diameter not existent? Hate when that happens. So the diameter is 0. Comp I is equal to 0. What's I? It this part too. Does it work for this? It does. Wait, so we have 2, 4, 4, 3. So D of 4 should not be 2. Or should it? Yeah, get comp isn't even the problem. The problem is like this. True, that should be included though. You're right. Actually, not sure how that worked. But it still doesn't make sense. Like this, a lot of this is wrong somehow, which is weird. Like everything's wrong. Di is something that exists. Diameter of G is max diameter of G dx. Just printing everything at this point, figuring out like what's happening. Can't really think about the code anymore. I don't think I'm capable of doing that, so that's sad. Oh, is that really it? That it should be G instead of I here? Damn. I guess that's it. Alright, but it's still wrong somehow because somehow this distance is... The distance from 4 is too much. Which I don't actually understand. So we start at 2 and we like... Distance at 4 is wrong. Why is the distance at 4 wrong? The distance at vertex 3, I suppose. 4 LX edge. This is going great. Doesn't compile. So close the bracket. Yeah. So 1 and 1. What is dp cur then? How would this be? Problem is that it's 2 somehow, but then it's like not. Something's messed up here. The curve equals max, dp next equals the maximum of its own thing, and this should be val minus 1. Because I'm sort of like pushing that wrong. guess that would do it. I'm gonna comment all this out instead of trying to fix it because it could still very well be wrong. I'm actually not sure how my huge sample didn't catch that. What else am I printing here? So I'm printing this. Alright, there is one more thing left, and that would be this. We can ask about this. We can just ask for all queries, basically. So we have 6 possible queries. 111, 114, 117. I'm not actually sure how to compute this, though. 11, 14, 11, 17, 14, 17. Right, okay. How do we know what's right and what's not? Nine, 12? The last 3 queries seem too big. It seems like a problem. Let's see. Those 2 queries definitely seem too big. Hi, Tron dude. How you doing? Yeah, 17. Okay, yeah. All of these are wrong. What the hell? Alright, wait. I'm gonna, I guess we can compute these by hand and then figure out what the hell is going on, because that is so wrong. I'm gonna go to the bathroom first. I'll be back again. No custom BRB screen this time, just like lame letters. Yeah. I have a feeling this is going to be more pain. Like, this implementation wouldn't be so bad if, like, my mind wasn't already, like, totally, fogged up from everything else, probably. And it would just, yeah, it's square root decomposition. But this would be, like, it wouldn't be that bad. Wouldn't be as bad. Okay, so, well, let's see if this makes sense. Alright, so in this first component, we have let's see. It's the value. Okay, wait. So let's look at the smaller ones first. So we have sum of the things is 2. Yeah, we have 2 2s and 1 1. So that makes sense in both of those. And then we have 2 1s in that. Yeah, that's what I'm doing right now. That's these two. So, like, 1 plus 2 is not 9. So that something's up with that. Like the 11 and 17, that's kind of concerning. So it's just like, get comp, this would be 3 and 4. Yeah. Okay. Now I can debug like this, I suppose. So let's first just look at I and then something like this. Maybe that's the problem, that I have to fix that in mixing. Should actually print the value. Still wrong, but less wrong. Interesting. That sort of divides it by 2. Actually, wait, is it wrong? It's like 2, 1. No, it's definitely wrong. Yeah, it's definitely wrong. Okay. Doesn't make any sense. So the number of things with 0 is nothing that's expected. Then the number of things with 1 would be, I think it should be diameter of B. Also, doesn't fix anything. Okay. So what's happening here is 2 and 2. Is that expected? We have, sounds about right, yeah. And whatever's happening here is some stuff. So I totally expect to be like B. Would be there are 2 ways to get diameter 3, 3 ways. Okay, so the answer would be actually this whole thing, but minus 1, which is surprising. I can do something like add these together. See what's wrong. It's gonna be hard to follow. Okay, 28 and then like 0. So what should it actually be? It should be 22. Should be, we have 2 ways to get 3. 4 ways to get 4, so it should be 22. Yet somehow it's not. So it's entirely the total that does this? Yeah, it's like 1 computation. And so the suffix here is 0. Because the minimum diameter is 1. 1 minus 1 is 0. Yeah, so anything will be greater when we do that. Wait, it's the maximum, right? Yeah, maximum. So it should be, wait, 1? No. Yeah, because S plus, like DI plus DJ will be greater than or equal to S. Then what? DI plus DJ plus 1 is equal to S. So like solve S minus 1 minus DI. Right. So suffix should be 0. Has B dot size should be 3. The diameter of B should be 2. The total should not be 28. So current frequency is 2, as expected. So current frequency plus the prefix sum should be 10. That's that. And then we do the frequency there. That's 6 times. Ah, wait. Wait. Okay, this should be I. Actually, we don't need to see sum at all. It's just I times the number of things that have this exact thing. Yeah, okay. Because what I was doing was I was multiplying the sum by the frequency. So I was taking the sum multiple times instead of the individual element multiple times. And that's dumb. Don't do that. Let's see if this works now. Comment out all this stuff. Let's see. Is 4 reasonable? I'm not going to verify the big ones. But is 4 reasonable? Or 4.3? So we have so we have 2. Let's see, like we have all these possible edges. We have 9 of these. So we have in this case, S never comes into play. Yeah, alright, I'll just submit, whatever. If it gets the wrong answer, then so be it. It's not actually that big a deal. I got rid of the debug prints, right? It's very likely to get wrong answer. Okay, wrong answer in test 15, which is like very far and much farther than I expected to get. Surprising. Fun. Okay, well, that's the next step, I guess. How big were the tests that we did? I guess like not that big, because test 15 is short. What would that even mean? That we pass some max tests, but not all of them? Let's see if it works on like the big thing. So I'm going to set k equals 1 and see if it gets the same results. Actually, it doesn't. Huh, okay, that's interesting. So something's wrong with pre-computation? It doesn't even make sense. Wait, what does it get before? How? Interesting. So what is it actually trying to do? Like, it is very nice that I'm bad at debugging. I know, I'm committed to this. I just want to finish with this. I'll be done. Wait, 1, 2, 1, 3, 1, 4. Large I is equal to count. I don't think we'll include G, because then it'll like, G is sort of exclusive, yeah. I equals 1. Starting from 1 because we're doing 1 indexing, I guess. Has I dot size greater than or equal to K. Large I is equal to count. I'm just committed at this point. I don't want to like, I just want this to work. Yes, I'm still on this problem. I'm that bad. Okay, what is this? Ah, right, okay. Right. Should be something like double. Okay. Does that do it? That was dumb. That was quite dumb. Come on. Float, do you want that? Past 15. Does it TLE? Oh my god. Finally. We got this thing. We got it. Yay. Alright. Okay, so, in total, solution, square decomposition. Find a way to solve this in O of min of the two sizes. Find a way to solve two components in O of min of the two sizes in with 2 pointers. Then once you do that, do square root decomposition to solve for pre-compute or don't pre-compute, like, yeah, and it's n square root n. Like, or n plus q root n. Like, you don't necessarily have to pre-compute, but like solve for things that have size greater than or equal to k. There are at most root n times n such pairs, and the rest of the pairs have their sizes being less than k, and therefore there are at most q root n work is done with that. Actually, there are at most n root n such pairs, but the idea is that for every blob, it takes O of n to compute in total, and there are root n blobs. So it's in total O of n root n. And here is O of q root n, so the total complexity is O of n plus q root n. Doing this sort of thing with 2 pointers requires computing diameters with dp, and specifically computing the farthest distance from each node with dp, then using 2 pointers with sort of prefix sums to compute these values. All of this sucks. My god. But that concludes everything. I guess, like, yeah, that's it. Interesting. Okay. Yeah, look at this, like, look at the length of this. You can avoid this part, as Everell said, by, like, just, like, saving answers, and that has the same effect. It's still n plus q root n, but whatever, it still works. So, almost 200 lines. That's fun. Alright, well, that was trees. That's all I got. This was a very hard tree problem. Hope you enjoyed watching me struggle on it. If I had started with it, it probably would have been much better. But I did not start with it, which is sad. So, yeah, okay. I'll have to end the stream now. That'll be good. Remember to subscribe. See you guys. It was 2,500. Float works because it's smaller in memory, so it doesn't MLE. Like, it uses less memory. Yeah, actually, sure. What other topics do people want? Can make that for the next poll. Alright, combinatorics, game theory, probability. Maybe I can have those separate. This thing was a probability problem, by the way. Just to note. Okay, yeah. I'll end the stream here. See you guys.